Mars has survived asteroid impacts, global dust storms, and 4 billion years of cosmic bombardment, but it has never faced anything like 3I Atlas. This interstellar wanderer carries ice and chemistry forged under an alien sun, and its approach to Mars represents humanity's first test of how well we understand cosmic threats from beyond our solar neighborhood. The October 3rd encounter could unfold as a routine gravitational dance, or it could trigger cascading catastrophes that transform Mars from our next home into our greatest warning. From impact scenarios that create 30 kilometers craters to contamination that introduces alien chemistry to an entire planet, the range of possible outcomes defies comfortable prediction. Tonight, we'll examine why the worst-case scenario might not involve Atlas hitting Mars at all, but something far more subtle and potentially permanent. Stay until the end to understand why the scariest outcome might not be impact at all, but something far more insidious. Part 1. October 3rd, the moment of truth. October 3rd, 2025. A date that will never repeat, etched now into calendars and whispered with equal parts awe and unease. On this ordinary Friday, the emptiness between planets will become a stage for an extraordinary performance, a celestial drama with the power to rewrite the very rules of planetary security. The interstellar wanderer known as 3I Atlas will sweep past Mars at a distance of 30 million kilometers. To earthbound minds, that span sounds reassuringly remote, about 75 times farther than the gulf between Earth and its moon. But in the theater of interstellar visitors, astronomers classify this as a perilous brush, a dangerously close pass. The European Space Agency has tracked the encounter with attention one usually reserves for disarming explosives. Their calculations reveal orbital patterns that look less like the graceful curves of clockwork astronomy and more like a fevered sketch of celestial mechanics gone astray. Atlas is not behaving like the disciplined comets bred in our solar system. It has been throwing tantrums since the day it was first detected, and October 3rd may be the moment its fragile composure finally collapses. The warning signs have been building like thunderheads on a summer horizon. Atlas has already released a carbon dioxide coma of staggering size, a spectral veil extending millions of kilometers in all directions. Most comets wait until far closer to the Sun to unveil such excess, but Atlas appears ignorant of the unspoken etiquette of the cosmos. Even more alarming are the sudden outbursts of brightness. Observatories across the globe have chronicled violent flare-ups that blaze without warning and fade into silence just as quickly. These are not the gentle, predictable brightenings of frozen bodies awakening to sunlight, but the erratic convulsions of something profoundly unstable, as if held together only by stubborn cosmic will. NASA's Sphere-X telescope has worked relentlessly to capture these fits, and the portrait that emerges would leave any planetary defense expert reaching for relief. The geometry of the plumes appears skewed, the emissions defy our models, and even its orbit shows subtle tremors hinting that this is no simple dirty snowball from the depths of another star. Now comes the truly unsettling twist. Atlas approaches its closest distance to Mars precisely as the planets slip into solar conjunction when Earth, the Sun, and Mars align in such a way that observation becomes nearly impossible. For weeks, astronomers will be peering into a blind spot just as the drama reaches its most critical act. It is like being asked to judge a high-stakes poker match while blindfolded, glimpsing only fragments through a keyhole. The timing feels mischievous, almost as though the universe itself delights in hiding the fate of our neighbor behind a curtain of glare. Within the scientific community, sober caution walks a tightrope above an undercurrent of dread. Astronomers know too well that sudden activity in comets often foreshadows fragmentation. When comas brighten wildly, when jets erupt in chaotic patterns, experienced eyes begin bracing for disintegration. Now imagine such a breakup, not in the distant safety of interstellar space, but within cosmic shouting distance of Mars. Visualize kilometer-sized shards of ancient ice and stone cast adrift, each threading its own dangerous path through the gravitational labyrinth of the inner system. Some fragments might plunge sunward, swelling the ranks of hazardous bodies. Others could be nudged into trajectories that intersect planetary orbits long thought stable. European Space Agency models warn that even without a direct strike, a shattering could scatter debris into corridors that cross Mars's path for years, even decades to come. What we face may not be a single brush with destiny, but the planting of a minefield that could haunt every future mission to Mars. And here lies the greatest mystery. We do not know what Atlas truly is. Its radiant coma blinds us to the heart within. It could be a single solid mass, a fragile collection of fragments barely held together, or some stranger configuration altogether. The very shroud that makes Atlas so breathtaking may conceal a time bomb ready to burst, strewing fragments across multiple orbits. NASA's Science Mission Directorate has remained careful in public statements, yet quiet preparations suggest that orbiters around Mars are being positioned, like cameras at the edge of a battlefield, to record whatever spectacle may come. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Trace Gas Orbiter serve as humanity's vigilant eyes and ears around the red planet. Should something extraordinary unfold on October 3rd, these silent guardians will be our only direct witnesses, archiving the evidence of an encounter that could alter forever how we comprehend visitors from beyond the stars. Yet, even these advanced machines are bound by the limits of their design. Their cameras and spectrometers were crafted to scrutinize Martian landscapes and trace atmospheric chemistry, not to chase fragments of high-velocity debris racing through the void. Their communication systems were engineered for scheduled data relays, not for the urgent cries of a planetary emergency. If 3i Atlas chooses to unleash a spectacle of cosmic violence, our fleet at Mars may find itself as startled and unprepared as the civilization that built it. And still, the promise of this investigation reaches far beyond idle curiosity. The task before us is to follow the evidence wherever it dares to lead. Even if that trail winds into territory that renders our assumptions about planetary safety fragile, perhaps even delusional, we will weigh the collision scenarios that haunt the dreams of planetary defense experts, imagining impact scars tens of kilometers wide gouged into Martian crust. We will examine atmospheric disruptions that might transform Mars into a toxic furnace, hostile not only to machines but to any hope of colonists yet to come. We will consider the contamination threat alien chemistry introduced into an environment that future generations hope to call home, an intrusion that could complicate exploration for centuries. Most unsettling of all, we will voice the questions that official bulletins rarely confront in public. What if Atlas is not merely drifting past? What if October 3rd marks not an incidental brush with another world, but the beginning of a chain of consequences far darker than a simple gravitational dance? The answers may surprise us, they may disturb us to the core, but one truth remains inescapable. After this date, our understanding of interstellar wanderers and our fragile place in their path will never be the same. The collision scenarios we are about to probe are merely the visible tip of a far deeper cosmic iceberg, one whose hidden mass stretches into the shadows of planetary catastrophe, daring us to imagine what lies beneath. Part 2. The collision scenario. The mathematics of planetary destruction possess a strange, almost austere elegance. When astronomers first run the numbers on the likelihood of 3i Atlas colliding with Mars on October 3rd, the results seem almost comforting. At a predicted distance of 0.19 to zero point 0.2 astronomical units, the geometry points toward an outcome that falls somewhere between vanishingly improbable and nearly impossible. Yet mathematics, much like democracy, depends on adherence to its own rules. And Atlas, as we have already witnessed, does not appear inclined to follow them. It behaves more like a cosmic anarchist than a disciplined traveler. Imagine, for a moment, a scenario in which one of those enigmatic fragmentation events we have discussed arrives at precisely the worst possible instant. Envision Atlas, holding itself together for 30,000 years across interstellar darkness, only to disintegrate like a brittle firework just as it enters Mars's gravitational domain. The parent body might sail harmlessly onward, continuing along the plotted path. But the fragments, those renegade shards of ancient ice and rock, would chart trajectories of their own. Each piece would inherit its own momentum, altered by the violent mechanics of the breakup. Some might surge toward the sun, others fling themselves outward to begin solitary odysseys into deep space. Yet a handful, perhaps only a few among hundreds, could find their roots bent just enough by Mars's gravity to convert a cosmic near-miss into a devastating strike. To grasp the danger, we must scale the destruction in human terms. A fragment between 100 and 500 meters in diameter, no larger than a city block, would strike Mars at velocities so immense that even rifle bullets would seem leisurely by comparison. The impact energy would rival the simultaneous detonation of thousands of nuclear warheads. The resulting crater would sprawl for kilometers, gouging the Martian crust and unleashing havoc. But that scar on the surface would only be the beginning of the planet's nightmare. Mars, cloaked in a tenuous atmosphere of carbon dioxide, has no real shield. Earth's thick air can burn smaller intruders and blunt the force of larger ones, but Mars is naked before the cosmos. Whatever energy is carried across millions of kilometers of empty space would be delivered directly, with nothing to soften the blow. The aftermath would reshape the planet into a scene scarcely recognizable to the orbiters and rovers that have chronicled its landscapes for decades. Shock waves would tear through rock layers, while ejector-pulverized stone mixed with ancient frozen water would be hurled high into the thin sky. From that single detonation, a global dust storm would ignite, dwarfing the seasonal tempests already infamous to planetary scientists. The opacity of the atmosphere would climb beyond any measurement in the historical record. Within hours, Mars would disappear beneath a suffocating shroud. Sunlight would vanish. Solar panels would be rendered useless. Temperatures would plunge in a nuclear winter effect that could linger not merely for months, but possibly for years. Yet dust is not the only menace. The impact would also release titanic bursts of electromagnetic energy, as charged particles from the expanding fireball tore through Mars's weak magnetic field. These surges could induce destructive currents in spacecraft electronics, crippling systems not designed for such punishment. The Mars Reconnaissance Orbiter, MAVEN, the Trace Gas Orbiter, and Mars Express, our robotic emissaries, circling the planet, would find themselves besieged in ways their engineers never imagined. Navigation systems could lose accuracy. Antennas might drown in static, overwhelmed by interference from an ionized debris cloud. Solar arrays could suffer from high-velocity particle strikes, each one a potential wound in the fragile lifelines of our machines. On the ground, the peril multiplies. Perseverance and curiosity, designed to endure typical Martian storms, would confront something entirely beyond their design parameters. A planet-wide dust hurricane, born from cosmic violence, would bury instruments and choke communication channels. Radio signals to Earth might flicker into silence. At the same time, radiation levels would spike. The impact would excavate subsurface material and blast it skyward, saturating the already meager atmosphere with charged particles. Mars, never blessed with Earth's protective magnetic field, would become even more hazardous for future explorers. Robotic systems would falter, vulnerable to radiation-induced errors. For human beings, such an environment would be uninhabitable, its dangers measured not only in days but in generations. And then comes the most chilling escalation. What if not one fragment, but many struck Mars? What if Atlas shattered into dozens of projectiles, each hundreds of meters across, each carrying the destructive force of its own apocalypse? Mars would not simply suffer a single wound. It would be riddled with scars, its surface convulsing under overlapping detonations. Multiple ejector clouds would collide and expand, turning the planet into a storm-racked cauldron. Electromagnetic chaos would smother communications, producing radio blackouts that might endure for months. Dust opacity could climb so high that Mars would be locked in a deep freeze, a planet-wide ice age altering its climate not for years, but for centuries. Such is the spectrum of possibilities when an interstellar anarchist defies the laws of celestial geometry. The numbers may comfort us with their improbability, but the cosmos rarely offers certainty. And on October 3rd, the red planet may stand as the unwilling stage for a drama written not by mathematics, but by chaos itself. And here the scenario grows deeply unsettling, even for those of us still circling Earth in safety. The gravitational turbulence born from multiple impacts could disturb the fragile orbits of Mars' two small moons, Phobos and Deimos. These jagged, irregular bodies are precarious to begin with. Phobos already creeps inward, along a slow spiral that will end in its destruction, though not for another 50 million years. Yet a violent disruption might hasten this destiny by unimaginable orders of magnitude. If ejecta from a colossal strike were to batter Phobos with enough force, or if Atlas fragments introduce destabilizing gravitational tugs, we might witness the death of a moon unfolding before our very eyes. The aftermath of such a calamity would be stark. Mars would gain a ring system, but nothing resembling Saturn's delicate, symmetrical bands. Instead, a turbulent swarm of shattered rock and dust would orbit the planet, a hazard field menacing spacecraft for centuries. The psychological weight on Earth would be immense. Mars has long been imagined as humanity's second horizon, the backup plan if Earth falters, the proving ground of our cosmic future. To see that world twisted into a radiation-soaked wasteland, encircled by the fragments of its own lost moon, would feel like watching the vision of tomorrow disintegrate in real time. And yet even this harrowing picture might not capture the darkest truth. Perhaps we have thought too narrowly, mistaking debris and destruction for the ultimate threat. What if October 3rd delivers not only rocks and ice, but something subtler, more insidious, an intrusion capable of poisoning Mars' habitability in ways we barely comprehend? The atmospheric shockwave scenario now before us demands attention, for it requires no fragment to touch the surface at all. Part 3. The atmospheric shockwave. Forget the comfortable images you carry of cosmic collisions. The most insidious dangers from 3I Atlas may never involve a single fragment striking the Martian surface. Mars's defenses, such as they are, verge on non-existent. Earth surrounds itself with a magnetic cocoon, a shield that bends and deflects the charged particles hurled outward by the sunday. Mars, by contrast, is exposed. Its global magnetic field perished billions of years ago, leaving behind only scattered patches of magnetism etched into its crust, fossil scars that whisper of a lost age of protection. Stripped bare, Mars is exquisitely vulnerable to forces that Earth's magnetosphere would dismiss with ease. When Atlas approaches, trailing its colossal carbon dioxide coma and perhaps fragments of ancient debris, The danger will not resemble the Hollywood spectacle of a shockwave flattening landscapes. No wall of compressed air will race across the desert plains at supersonic speed. Instead, the threat manifests in subtler, more enduring form, an electromagnetic and particle cascade capable of rewriting Mars's atmospheric chemistry and electrical environment for months or even years. Picture Atlas as it nears the planet, its nucleus convulsing, venting volatile gases and dust in erratic bursts we have documented throughout 2025. Each eruption expels clouds of ionized plasma that dance with the solar wind. As this charged torrent collides with Mars's patchy magnetic remnants, it does not rebound, it penetrates, it spirals. It generates whirling electromagnetic eddies that could linger long after the comet itself has vanished into the dark. The most immediate sign of this invisible intrusion would be spectacular light. Mars's occasional auroras, faint and localized, could erupt into planet-wide storms. Instead of delicate ribbons like Earth's northern lights, these displays would rage as chaotic sheets of fire across the skies, dazzling but destructive, disrupting radio signals and endangering electronics. Yet even such brilliant storms are only the surface. The deeper turmoil would occur in the ionosphere, the charged upper layer that spacecraft depend upon for communications. Atlas's plasma could distort this fragile shell, creating blackout zones that persist for weeks. Imagine the implications. Rovers like Perseverance and Curiosity rely on meticulously scheduled uplinks to transmit data and receive commands. A sustained disruption would sever those digital lifelines, marooning billion-dollar explorers in silence, unable to speak or listen across the gulf of space. Nor would the chaos confine itself above. Mars's thin atmosphere makes it particularly vulnerable to electrostatic upheaval. As Atlas's debris interacts with dust already swirling across the surface, storms could emerge charged with immense electrical potential. Picture towering whirlwinds, their grains crackling with power, discharging bolts of lightning that dwarf anything witnessed on Earth. These would not be gentle static flickers, but violent electrical arcs, capable of frying instruments, shattering communication, and turning the Martian surface into a theater of electric fury. The scenario darkens further when we recall Mars's penchant for global dust storms. Entire planets shrouded, solar panels buried, skies opaque for months. These cataclysms can be sparked by the smallest atmospheric imbalance. The electromagnetic disarray from Atlas might provide exactly the nudge required to tip Mars's weather into such a planetary convulsion. But here is where the physics grows even more disturbing. What if Atlas does not simply trigger another dust storm, but initiates a phenomenon without precedent in planetary science? Imagine the comet's charged particles seeding a self-sustaining feedback loop. It begins with disturbances high in the ionosphere, cascades downward as static electricity charges the fine dust below, and then lifts that dust skyward in greater volume. The increased haze alters energy balances, amplifying temperature and pressure differences. Those differences, in turn, feed the storm further, sustaining and intensifying it long after the comet has moved on. What would emerge is no longer a passing tempest, but a new climate state, a storm engine powered by electromagnetic forces and atmospheric dynamics locked together in a vicious embrace. Mars could find itself trapped in an endless cycle, its skies permanently thickened, its surface darkened, its atmosphere rewritten by the legacy of a visitor from another star. Meanwhile, the charged dust continues its dance with the faint magnetic remnants scattered across Mars, sustaining the electromagnetic chaos. The outcome would be a planet caught in a near-permanent state of meteorological and electrical unrest, a feedback loop from hell that could endure long after 3i Atlas has vanished into the outer reaches of the solar system. Mars would become a world of endless tempests, where dust storms never truly subside, where radio communication flickers unreliably, and where the radiation environment grows so erratic that even the toughest robotic explorers might finally fail. Engineers at NASA designed spacecraft to endure the known hazards of Mars, but no blueprint ever prepared them for a global electromagnetic tornado. The Mars Reconnaissance Orbiter's high-gain antenna could find itself constantly battling interference from electrically charged clouds. MAVEN's particle instruments, tuned for subtle interactions with the solar wind, might be overwhelmed by the cacophony of particles stirred up in Atlas's wake. The public response would be instant and disorienting. As images from Mars arrived sporadically, and as familiar communication windows collapsed, speculation would surge. Social media would ignite with theories about the fate of our machines. Cosmic catastrophes, concealed disasters, conspiracies cloaked in silence. Official statements, filled with technical detail and calm denials, would be drowned beneath the roar of more sensational narratives. The most troubling dimension, however, would lie in perception. Mars would not be burning in any ordinary sense. Its atmosphere, dominated by carbon dioxide, cannot sustain combustion the way Earth's oxygen-rich skies do. Yet the spectacle of global auroras flaring like wounded skies, lightning storms arcing through dust-choked air, and strange electromagnetic phenomena would conspire to create an illusion of planetary fire. To the watching world, Mars might appear to have ignited a cosmic inferno captured in distorted broadcasts. Scientists would struggle to explain the paradox. Mars had not chemically caught flame, but it had been rendered temporarily uninhabitable for explorers all the same. The distinction between a world aflame and a world unraveled by electrical violence would be lost on a public shaped by disaster films and apocalyptic imagination. And yet, as fearsome as these electromagnetic nightmares sound, they may not define the worst outcome. What if Atlas does not only deliver storms of particles and dust? What if the true danger lies in contamination, alien material seeded into Mars, persistent across ages, reshaping its destiny? Unlike electromagnetic tempests that fade like summer squalls, a biological intrusion could alter Mars forever, and in doing so, change the course of humanity's future among the stars. Part 4. Contamination from another star. The idea of panspermia, the notion that life can hitch a ride between worlds on fragments of cosmic debris, has fascinated and unsettled scientists for generations. Yet when that debris emerges, not from our own solar family, but from the depths of another star system, the implications grow heavy enough to rob astrobiologists of sleep. 3I Atlas confronts us with precisely this possibility, one so troubling that few within the scientific establishment seem willing to address it openly. This wandering body has drifted through interstellar night for at least 30,000 years, its frozen nucleus serving as a cosmic vault, preserving whatever molecular cargo it may have carried from the alien nursery of its birth. The enormous carbon dioxide coma Atlas has unfurled around itself provides far more than a spectacular display. Carbon dioxide is not merely a waste gas. It is an unusually effective solvent for organic chemistry, capable of stabilizing intricate molecular structures through a wide range of temperatures and pressures. Within that billowing shroud, fragile compounds could have survived across eons of travel, perhaps even engaging in slow chemical evolution spurred on by the ceaseless radiation of deep space. In effect, Atlas has become a drifting laboratory, a vessel for experiments neither designed nor observed by human eyes. NASA's James Webb Space Telescope has already turned its instruments toward this enigmatic visitor, teasing out spectral fingerprints from its coma. The results remain tentative, layered in technical caution, yet they point to carbon dioxide, water vapor, and what researchers carefully label complex organics. Behind the diplomatic phrasing lies a more unsettling truth. These molecules may not resemble anything formed within our solar system. Meanwhile, the SphereX mission has charted patterns in Atlas's emissions that do not match the familiar behavior of comets awakening in sunlight. Instead of straightforward sublimation, the data hints at active chemistry reactions slowly unfolding within the coma itself, possibly driven by radiation or ancient catalysts lingering since formation. Planetary protection guidelines exist precisely to guard against cross-contamination between worlds. But these rules were drafted for human spacecraft and robotic landers, not for the uncontrolled arrival of an entire interstellar body. Atlas carries no sterilization protocol. If its October 3rd encounter delivers exotic molecules to the Martian surface, they may mingle with soil and atmosphere in ways our models cannot anticipate. They could catalyze strange reactions, destabilize the chemical balance of the planet, or imprint molecular templates that confuse our search for indigenous Martian biology. For planetary protection specialists, one scenario is especially nightmarish: alien organic compounds settling into the Martian regolith and assembling into structures that mimic the hallmarks of life. These pseudo-biological systems would not be alive as we define it, but they might still consume resources, alter chemistry, and spread through natural processes. In such a case, Mars could become unfit for colonization long before human settlers ever arrive. Imagine attempting to build life support systems on a world where the soil itself carries replicating chemistry that resists both understanding and control. The risk assessments for every planned mission would need to be rewritten from scratch. Even more insidious is the danger of scientific confusion. Mars exploration has long been driven by the dream of detecting life, past or present. Instruments are already being engineered for sample return missions, calibrated to identify faint chemical whispers of biological activity. But what happens when those tools confront molecules seeded not by Mars but by Atlas? How would we tell native signatures apart from contamination carried across the interstellar gulf? The possibility of false positives looms large. Entire decades of scientific progress could be jeopardized as researchers struggle to separate authentic Martian evidence from imported chemical noise. The contamination scenario darkens further when we consider how easily Mars's climate could distribute foreign material. Should Atlas's approach ignite a global dust storm, any deposited organics might be lofted into the atmosphere and scattered worldwide within weeks. What begins as a localized deposit could become a planetary phenomenon, embedding itself at every future landing site, complicating every experiment, shadowing every attempt to prove or disprove life on the red planet. NASA's roadmap still points toward human missions to Mars in the 2030s, bold ventures meant to establish a foothold for our species beyond Earth. But that vision assumes a planet chemically stable and biologically sterile. If Atlas delivers contamination from another star, Mars may transform from our second chance at survival into a proving ground for a cosmic truth. That life, or something uncomfortably close to it, does not always respect the boundaries we imagine between worlds. Human missions to Mars rest on a fragile assumption that the planet will provide a reasonably predictable stage upon which life support systems can operate with confidence, and where in situ resource utilization can draw water, oxygen, and even fuel from local materials. Yet organic contamination from 3I Atlas could shatter those expectations entirely. Water extraction systems designed to process pristine ice might choke with alien compounds. Atmospheric processors built for a narrow band of chemistry could be overwhelmed by reactions they were never meant to endure. Even the psychological toll on human pioneers would be immense. Imagine the first footsteps on Martian soil, only to discover that the environment has been rewritten by an interstellar interloper. The unsettling truth is that the timeline for recognizing these effects might stretch far beyond the horizon of current missions. Craters or electromagnetic storms reveal their violence instantly, but chemical and biological contamination is insidious, unfolding across decades. It is conceivable that we might not fully grasp what Atlas has seeded into Mars until the 2060 seconds, or even later. Such uncertainty places the scientific community in a deeply uncomfortable position. To admit the risk openly might sound like fear-mongering, eroding fragile public support for exploration programs painstakingly built over decades at the cost of billions. To remain silent, however, risks sending future missions into an environment that may no longer resemble the Mars described in our models. International law offers little comfort here. The Outer Space Treaty and related accords were drafted to manage human-caused contamination, not cosmic delivery of alien chemistry. Should Atlas seed Mars with exotic molecules, no framework exists to assign responsibility or coordinate a global response. The issue extends beyond law into ethics. Do we possess the right to press forward with exploration if the ground we tread may already be compromised by forces beyond our control? Should ambitious missions be delayed until the consequences of Atlas are understood? These questions are not only technical, they are moral, and their answers could redefine humanity's relationship with planetary exploration for generations. And yet, as daunting as biological nightmares may be, Atlas reminds us that physics itself can turn treacherous. The gravitational ballet of planets, moons, and drifting debris can generate outcomes more catastrophic than contamination alone. What if the October 3rd passage does not merely change Mars's chemistry, but unsettles the gravitational harmony that has governed the Martian system for billions of years? The orbital chaos scenario that follows makes even the prospect of biological contamination seem almost modest by comparison. Part 5. Orbital Chaos. Phobos and Deimos, the two diminutive companions of Mars, have long been described by astronomers as cosmic captives, asteroidal strays, seized by the planet's gravity in some forgotten chapter of the solar system's past. Yet these celestial prisoners are anything but stable. Phobos, the larger and closer of the pair, is already doomed. It circles Mars on a slow inward spiral, fated to crash into the planet in roughly 50 million years. Under ordinary circumstances, this timescale offers humanity more than enough breathing room. Centuries to colonize Mars, millennia to plan, eons to ponder how to deal with the eventual collapse. But the approach of 3I Atlas on October 3rd may introduce variables that hasten this cosmic executioner's schedule in ways we have never considered. The gravitational paradox is striking. At 30 million kilometers, Atlas's pull on the Martian moons is vanishingly small. It would be like a skyscraper on Earth, attempting to tug the moon from its orbit. The raw mathematics insist Atlas cannot simply reach out with invisible hands and hurl Phobos or Deimos into chaos. Yet mathematics alone does not always capture the full complexity of unstable systems. Chaos theory warns us that when a body is already teetering on the edge, even the gentlest nudge can produce outsized consequences. Phobos, as fate would have it, is precisely such a body. Orbiting a mere 6,000 kilometers above Mars, Phobos circles the planet 3 times in a single Martian day. Its proximity places it deep within the Roche limit, the region where tidal stresses from Mars exceed the Moon's ability to hold itself together. Only the internal strength of its fractured, porous rock prevents it from crumbling instantly. Even so, that strength is failing. Recent imagery has revealed long, parallel grooves etched across Phobos's surface, scars of stress that may mark the opening stages of its tidal breakup. The Moon is being pulled apart grain by grain, orbit by orbit, in a slow-motion death spiral that has endured for millions of years. Now introduce Atlas into this fragile ballet. The comet's gravity may be negligible, but it carries something far more dangerous: debris. As Atlas hurtles through Mars's wider gravitational neighborhood, it could shed material that crosses the orbital paths of Phobos and Deimos. Even the smallest grains, traveling at interstellar velocities, carry unimaginable force. A particle no larger than a grain of sand, slamming into Phobos at 20 kilometers per second, would strike with the violence of a hand grenade. Multiply such collisions by thousands or millions, and the result could become catastrophic. The cumulative stress of this bombardment could drive Phobos past the breaking point. Instead of gradually succumbing to tidal forces over geological epochs, the Moon might shatter suddenly during, or in the aftermath of, Atlas's passage. What had been a demolition project unfolding over millions of years could collapse into a single moment of ruin. A moon once destined for a slow death might instead explode into a cloud of fragments, its long twilight cut short by the brush of an interstellar visitor. And from this destruction could rise something unprecedented in planetary science. What if the demise of Phobos does not simply erase a moon, but creates a ring? Imagine Mars girdled by a vast halo of debris, shimmering against the dark. This would not be the delicate symmetry of Saturn's ancient rings, honed over millions of years into luminous order. Planetary ring systems are extraordinarily complex. Their stability, the product of countless collisions, gravitational balances, and electromagnetic interactions. A sudden ring birthed by Phobos's collapse would be nothing like Saturn's masterpiece. Instead, Mars might find itself encircled by a violent, chaotic storm of rock and dust, an unstable wreath that endangers spacecraft and complicates exploration for centuries. For future astronauts, such a ring would be less a wonder than a warning, a reminder of how fragile the structures of the solar system truly are. Atlas may not touch Mars directly, yet its passage could rewrite the destiny of its moons, transforming one doomed companion into a planetary ring and altering the face of the red planet for ages to come. A ring system born from the violent disintegration of Phobos would bear little resemblance to Saturn's serene, shimmering bands of ice and dust. Instead, Mars would become encircled by a storm of fragments moving in chaotic, elongated orbits. Some shards would be massive enough to cripple any spacecraft caught in their path, while others, no larger than grains of sand, would create a relentless micrometeoroid environment. Over time, these tiny missiles would scour solar panels, pit metallic surfaces, and scratch delicate optical instruments, steadily eroding the technological lifelines of future explorers. For mission planners, the challenge would escalate from managing the predictable orbits of two small moons to navigating a minefield of thousands of wandering objects, each following a trajectory that defies long-term forecasting. The collision risks would multiply exponentially, making routine operations in Mars orbit not just dangerous but perhaps impossible. The dream of establishing a bustling highway of spacecraft around the red planet could collapse into a nightmare of constant hazard avoidance. Orbital mechanics compounds the cruelty. Unlike terrestrial pollution, which human ingenuity can sometimes clean or contain, orbital debris is governed by the unyielding equations of celestial dynamics. Every impact between fragments spawns more fragments, each carving its own path. The process accelerates, feeding upon itself, creating cascading destruction that can endure for centuries. Spaceflight engineers have long dreaded this runaway chain reaction, under the name of the Kessler syndrome. While Earth's orbital environment has always been the prime concern, Mars, with its weaker gravity and thin, ineffective atmosphere, may be even more susceptible. Here, debris would linger far longer, resisting natural cleanup mechanisms that slowly remove low-altitude junk around Earth. The psychological blow to humanity's aspirations would be immense. For generations, Mars has been imagined as our fallback world, the next great frontier where civilization could be rebuilt if Earth falters. To see that vision literally torn apart, replaced by a deadly halo of wreckage, would feel like watching humanity's future dissolve before our eyes. The red planet, long a symbol of possibility, would instead stand as a warning of how fragile those dreams truly are. The timescales only deepen the despair. While dust storms fade and even chemical contamination may eventually disperse, orbital debris obeys the slow, merciless laws of mechanics. Shards from Phobos's catastrophic end could continue circling Mars not merely for decades, but for millennia, perhaps millions of years, locking the planet in a prison of its own shattered moon. For future explorers, Mars would no longer be a beacon of hope, but a fortress surrounded by a moat of cosmic shrapnel. And yet, even this grim picture may be too parochial. Perhaps we are thinking too narrowly, imagining Atlas's consequences confined to the Martian system. What if October 3rd marks not an isolated disaster, but the first link in a chain of gravitational reverberations stretching across the solar system? Orbital perturbations operate with a patience that mocks human planning horizons. A tiny nudge delivered today may unfold as catastrophe only after decades, centuries, or longer. The comet's passage could seed instability that, given time, ripples outward, reshaping orbits far beyond Mars. As we turn to examine the possibility of such a chain reaction, we must confront a sobering prospect: that Atlas's fleeting encounter with Mars may not end with the red planet at all. It may instead serve as the opening move in a cosmic game whose final consequence threatens not only Mars's fragile moons or our robotic emissaries, but Earth itself. Part 6. The Chain Reaction to Earth. In the language of the cosmos, distance offers comfort, but only the illusion of safety. According to NASA's latest projections, 3I Atlas will make its closest approach to Earth in December 2025, sliding past at roughly 1.8 astronomical units, about 270 million kilometers. By any ordinary standard, this seems like a margin wide enough to dismiss fear. Yet the solar system does not obey ordinary logic. It is a web of interlocking gravitational tethers, where the faintest pull can ripple outward in ways that unfold not in days, but across decades or even centuries. What happens at Mars in October will not remain confined to Mars. Its consequences will radiate outward, woven into the invisible architecture of celestial mechanics. Orbital perturbation theory explains this unsettling truth. Every gravitational meeting, no matter how slight, adjusts the paths of the bodies involved. Atlas brushing past Mars will inevitably alter both of their orbits. The change is tiny, measured in mere meters per second against velocities usually reckoned in kilometers per second. At first glance, the shift seems negligible. Yet when these small corrections align with resonant regions of the solar system, their influence multiplies. Just as the rhythmic push of a finger can set a massive pendulum into full swing, so can tiny orbital nudges compound until, generations later, trajectories have shifted by thousands of kilometers. The first concern is debris. Should Atlas fracture as it nears Mars, as some scenarios suggest, its splintered remains will not vanish when the encounter ends. Each fragment will continue on its altered course, threading new paths through the inner solar system. Astronomers use a polite term for this outcome: a persistent hazard environment. Some pieces may find themselves captured in resonances with Earth's orbit, ensuring periodic near misses that recur for decades. Others may slip into elongated orbits that drag them deep into the solar system before slingshotting back at unpredictable times. In either case, the quiet background of objects that threaten Earth would swell, the danger distributed not in a single crisis, but across centuries of vigilance. Modern planetary defense systems represent triumphs of engineering. Projects like the Asteroid Terrestrial Impact Last Alert System, PANSTARRS, and the upcoming Legacy Survey of Space and Time have given us unprecedented ability to catalog objects and forecast impacts. Yet all these systems were designed for asteroids born within the solar system, their orbits relatively well-behaved and predictable. Atlas fragments would not conform to these patterns. They would arrive on erratic trajectories, their velocities skewed by interstellar origins and multiple gravitational brushes. Their composition, alien to our classification systems, might confuse the algorithms designed to sort threat from harmless wanderer. The danger here lies in time itself. Unlike the violence of an immediate impact, gravitational perturbations operate across what physicists call secular timescales, slow, steady accumulations of change that reveal their true force only after decades. The October 2025 encounter might not reveal its consequences until the 2040 seconds or later, when Earth begins crossing paths with fragments that no one thought dangerous. This time lag produces a particularly insidious form of risk. The leaders tasked with funding planetary defense today will not be alive to face the consequences of their decisions. The bill for neglect may not arrive until the middle of the century, or even beyond. Adding to the unpredictability is a subtle phenomenon called the Yarkovsky effect. Small bodies absorb sunlight during the day, then re-radiate that heat at night, creating a minuscule but steady thrust. Over years, this thermal recoil alters orbits dramatically. For fragments of Atlas potentially composed of exotic materials with unfamiliar thermal properties, the Yarkovsky effect could lead to orbital migrations that escape our models entirely. Picture, then, a nightmare unraveling over half a century. Atlas splinters, and simulations dismiss the fragments as harmless. But as decades pass, sunlight itself nudges them along trajectories no one foresaw. By the time ground-based telescopes detect their migration into Earth-threatening paths, humanity could find itself without the decades of warning normally required to mount a deflection mission. The illusion of safety would vanish, replaced by the stark realization that a fleeting encounter at Mars had planted the seeds of a disaster destined to bloom in Earth's skies generations later. The precedent for cascading gravitational disasters is etched deep in our solar system's past. Roughly 4 billion years ago, during what scientists call the Late Heavy Bombardment, resonant shifts in the orbits of the outer planets may have destabilized vast populations of comets and asteroids, hurling them inward in a storm of impacts. The battered surface of our moon still bears the scars of that era. Every crater, a silent monument to the chaos that once turned the inner solar system into a cosmic shooting gallery. But 3I Atlas brings with it variables the Late Heavy Bombardment never included: interstellar velocities, unfamiliar chemical compositions, and fragmentation behaviors that defy the rules written by billions of years of solar system history. We may be staring into the face of a new kind of gravitational cascade, one for which we possess neither precedent nor reliable models. The meteor shower implications alone are chilling. Every year, Earth drifts through the dusty trails left by long-dead comets, producing predictable spectacles such as the Perseids and the Geminids. These showers delight stargazers and pose little danger. Their grains are too small, their entry speeds too modest, to do more than streak harmlessly across the sky. Atlas fragments, however, would not behave so gently. Traveling at interstellar velocities and perhaps composed of exotic materials unlike any meteoroids we know, they could trigger airbursts rivaling the Tunguska explosion of 1908. That event, caused by an object only 30 to 60 meters wide, flattened 2,000 square kilometers of Siberian forest in an instant. Now imagine Earth passing repeatedly through Atlas debris streams, each crossing spawning Tunguska-class detonations. The cumulative effect could ravage continents, not in a single blow but through decades of recurring catastrophe. Modern civilization is far more vulnerable to such events than the world of 1908. Our power grids, communication networks, and transportation systems create interdependent webs where a single failure can cascade into systemic collapse. An airburst over a major city could cripple economic systems for years, leaving scars not just in landscapes but in societies. Insurance markets have already begun to consider the costs of cosmic risk. Firms like Lloyd's of London model space weather disruptions and satellite failures. Yet these assessments assume years of warning before a major impact, time enough for evacuations and infrastructure reinforcement. Atlas fragments would not grant such luxury. Their chaotic orbits, shaped by interstellar speeds and unpredictable gravitational encounters, could give us warning times measured not in decades, but in days or hours. The financial consequences might dwarf the physical ones. An elevated background of unpredictable meteor storms could create a death corridor of risk lasting decades, undermining investment, destabilizing markets, and straining emergency management systems. Humanity could find itself living not under the shadow of a single apocalypse, but in a prolonged state of cosmic siege. Perhaps most disturbing is the thought that this process has already begun. The gravitational perturbations that will define Atlas's long-term influence may have been set in motion months ago, when the comet first entered the solar system's sphere of influence. Orbital mechanics is deterministic chaos. Once the initial conditions are established, the pathways are inevitable, even if the outcomes appear random to human eyes. We may already be living through the opening act of a gravitational cascade whose consequences will not fully reveal themselves for centuries. Even our early warning systems, impressive as they are, carry vulnerabilities. Ground-based telescopes are hindered by weather and atmospheric distortion. Space-based observatories could themselves fall victim to debris fields. Communication links that carry alerts to defense networks might be disrupted by the electromagnetic storms we explored in Mars scenarios. And even if our sensors function perfectly, spotting every Atlas fragment decades before it becomes a threat, we face the sobering truth that our deflection capabilities remain primitive. The DART mission demonstrated that we can nudge a small asteroid, but under controlled circumstances. A well-characterized target, predictable composition, and a clean orbital track. Atlas fragments would be another matter, entirely chaotic, fast-moving, and composed of materials we do not yet understand. They may not respond to impacts or deflections as our models predict. The nightmare is not sudden planetary annihilation, but the agonizing knowledge of danger without remedy. We could foresee catastrophe decades in advance, and yet stand powerless, watching our neighborhood grow steadily more hostile. This is the true horror of the chain reaction scenario. Not fiery spectacle, but slow, relentless destabilization unfolding across timelines that stretch far beyond the span of human political or economic planning. We may already be witnessing humanity's first self-inflicted cosmic crisis, born of our expansion into a solar system that was never as stable as we believed. At the same time, our focus cannot remain fixed solely on Earth's long-term fate. Our robotic emissaries at Mars, The spacecraft that represent humanity's eyes and ears on another world face more immediate perils. They were engineered under assumptions that never accounted for interstellar chaos. What happens when cutting-edge space technology encounters forces that obey no rules familiar to Earth? Part 2. Spacecraft at Risk. Space, despite the poetic visions of science fiction, is a profoundly hostile arena for the fragile electronic systems that carry humanity's presence beyond Earth's protective cocoon. Each spacecraft is a monument to engineering precision, a lattice of sensors, processors, and communication arrays designed to perform flawlessly in an environment where even a single failure can doom an entire mission. Mars' orbit, though less punishing than the infernal magnetosphere of Jupiter, offers its own brutal challenges. Radiation gnaws at circuitry, steadily eroding electronic lifespans. Micrometeoroids, rare but merciless, strike with pinpoint lethality, capable of crippling essential systems. Temperatures swing violently between the deep cold of shadow and the searing heat of unfiltered sunlight, stressing even the toughest alloys until fatigue spreads like cracks through bone. The orbiters currently circling Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter were engineered to endure these known adversities. They were not designed, however, to confront the turbulence that 3I Atlas may bring. These machines were calibrated for Mars under normal conditions, not for survival in the chaos of interstellar debris and electromagnetic storms. The vulnerabilities lie deep within their very architecture. High-voltage power systems, indispensable for running sophisticated instruments across the gulf of space, could turn treacherous in an unstable electromagnetic environment. Charged particles accelerated by Atlas's passage might build static differentials strong enough to arc across circuit boards, vaporizing components that took years to perfect. Consider the Mars Reconnaissance Orbiter, launched in 2005 and still carrying some of the finest imaging and communications hardware ever sent to another planet. Its high-rise camera can capture surface details smaller than a meter, while its radio science experiments probe the atmospheric layers of Mars with extraordinary precision. But this remarkable machine depends on star trackers, optical sensors, that determine spacecraft orientation by watching the stars. A debris cloud from Atlas could blind or confuse these trackers, filling their vision with false targets or floods of stray light. Without reliable attitude control, the orbiter could lose its ability to aim its high-gain antenna at Earth, silencing its stream of discoveries. MAVEN, the Mars Atmosphere and Volatile Evolution mission, confronts a different peril. It was built to study how the solar wind strips Mars's atmosphere, relying on finely tuned particle detectors and magnetometers. Atlas, however, could unleash torrents of particles far beyond MAVEN's calibration. It would be like attempting to measure a breeze, with instruments suddenly thrust into a hurricane. Such overload could damage the sensors permanently, leaving them blind at the very moment their data would be most valuable. Electromagnetic surges present another layer of threat. While not the dramatic EMP weapons of thrillers, a sudden spike in the local electromagnetic field could still be devastating. Spacecraft wiring, spanning thousands of meters, can act like antennas, gathering energy and channeling it into destructive currents. What powers life in space could just as easily become the path of its death. Mars Express, the European Space Agency's seasoned explorer, has circled the planet since 2004. After 2 decades of service, its systems already strain against time. Components operating near their limits might not endure the extra burden imposed by Atlas-driven chaos. A spacecraft that has survived countless Martian winters might finally falter under stresses no designer foresaw. The Trace Gas Orbiter, the most modern of the fleet, carries instruments capable of detecting trace gases in the Martian air, including tantalizing biosignatures. But these sensors demand pristine stability to separate authentic signals from background noise. A flood of electromagnetic interference would swamp their readings, turning data into meaningless static. Years of careful observations could be rendered worthless in an instant. Each spacecraft embodies human ingenuity, stretched to the edge of possibility. Yet all were conceived in a world that never imagined the passage of an interstellar anarchist like Atlas. Their designers built them to withstand Mars as we understood it, not the chaos of a cosmic visitor rewriting the rules. Should Atlas unleash its fury, our emissaries at the Red Planet may find themselves struggling against an environment that no simulation, no test chamber, and no engineer ever prepared them to face. Electromagnetic interference threatens more than temporary data loss. It could corrupt the calibration systems of sensitive spectrometers, requiring complex recalibration procedures that may be impossible to execute across interplanetary distances. Escalating this to its most catastrophic conclusion raises a disturbing question. What if Atlas's passage does not merely jeopardize individual spacecraft, but destabilizes the entire orbital network around Mars? What if electromagnetic turbulence grows so severe that every orbiter slips into safe mode, effectively blinding humanity's robotic presence at the Red Planet? Safe mode was designed as the ultimate fallback, a protective shell intended to preserve spacecraft when sensors detect conditions outside expected parameters. In this state, non-essential systems power down, solar panels rotate to face the sun for maximum energy collection, and the spacecraft awaits instructions from Earth. The assumption behind this safeguard is that anomalies are temporary, and ground controllers will eventually restore normal operations. But what happens if the chaos persists for weeks, or even months? In that scenario, our orbiters could remain trapped in limbo, silent guardians, unable to conduct science, unable even to serve as relays for the surface rovers. The psychological impact on global Mars exploration efforts would be enormous. Imagine the headlines announcing that every Mars orbiter has gone silent at once. Social media would erupt in speculation, awash with conspiracy theories about cover-ups, cosmic disasters, or failed secret missions. The fragile reservoir of public support, built patiently through decades of iconic images and steady progress, could drain away almost overnight. For mission controllers at JPL and partner agencies, the situation would present an unprecedented management crisis. Standard recovery protocols assume two critical conditions: communication with the spacecraft and an environment that allows diagnostics to be performed. Electromagnetic interference could strip both away, leaving engineers staring helplessly at blank telemetry screens, powerless to guide their machines through the storm. The ripple effects would cascade quickly to the Martian surface. Perseverance and Curiosity, the rovers that have become symbols of exploration itself, rely on orbital relays for their steady conversation with Earth. Without those networks, the rovers would be forced to use their own limited radios to speak directly across the void. Data rates would plummet. Operational flexibility would collapse. Science operations carefully planned for years in advance would grind down to a trickle. There is another layer of danger. Atlas might coincide with the rarest and most dreaded of cosmic events, a coupling between a comet-driven particle storm and a major solar outburst, whether a coronal mass ejection or a surge of energetic particles. Shielding systems on Mars spacecraft were designed to handle either of these threats in isolation, not both together. A dual assault could overwhelm defenses, saturating detectors, frying circuitry, and crippling systems beyond repair. The recovery timeline in such a scenario would stretch into years. Unlike terrestrial infrastructure, which can be patched by sending technicians into the field, spacecraft orbiting Mars must be diagnosed and repaired remotely across a gulf of hundreds of millions of kilometers. Each command sent from Earth takes minutes to arrive, each response minutes to return, dragging out even the simplest troubleshooting steps. Some spacecraft would never recover. Components damaged by electrical surges or degraded by sustained particle bombardment may never respond to commands, consigning missions that survived for decades to sudden, catastrophic ends. The consequences would reach far beyond the machines themselves. Long-term investigations into Martian climate change, atmospheric evolution, and geological processes would be abruptly cut short. Research programs designed to span decades would be interrupted midstream, leaving gaps in the continuity of scientific records that may never be filled. Future missions, planned with the assumption of reliable orbital assets, would be forced back to the drawing board. Perhaps most ominous of all, the collapse of Mars's orbital fleet would rob humanity of its ability to observe Atlas's effects in real time. We would know that something dramatic had happened, but the details would remain hidden behind silence. To piece together what transpired, new missions would have to be conceived, built, and launched, a process that consumes at least a decade. By then, whatever transformations Atlas wrought on Mars may already be complete, their evidence altered or erased by time. The nightmare grows deeper when one remembers that Atlas does not operate in isolation. It moves within the interconnected machinery of solar system dynamics, where even the Sun itself can feel the influence of dramatic encounters. What if October 3rd marks not just a crisis for Mars and its orbiters, but the opening act of a solar weather catastrophe, one capable of reshaping conditions across every world bound to our star? Part 8. Radiation storms and solar chaos. The Sun, despite its reassuring glow, is not a symbol of stability, but a barely restrained fusion engine, balanced on the knife's edge between equilibrium and chaos. Its behavior follows an 11-year rhythm of activity, cycles that give rise to electromagnetic storms capable of disrupting technology across the solar system. Even so, these periodic tempests may pale before what could unfold if 3I Atlas sweeps through the inner system at the very moment our star approaches peak activity. Atlas will reach perihelion in late October 2025, passing at a distance of roughly 1.4 astronomical units. This keeps it outside the suicidal path of sungrazers that dive directly into the corona, yet well within the region where the solar wind roars outward with volatile intensity. Under normal circumstances, the physics of comet-solar-wind interaction are straightforward. As a comet draws closer to the Sun, radiation sublimates its frozen crust, producing the glowing coma and tails that trail away into space. The solar wind, racing outward at more than 400 kilometers per second, shapes these emissions into the luminous anti-sunward plumes that have haunted human imagination for millennia. But Atlas is no ordinary comet. Its immense carbon dioxide coma and its unpredictable surges in brightness suggest processes that refuse to conform to conventional cometary models. An object behaving in unfamiliar ways, encountering the Sun's tangled electromagnetic environment, raises the prospect of outcomes beyond prediction. Consider its ion tail, vast streams of charged particles accelerated by the solar wind, stretching millions of kilometers into the void during perihelion. This tail is not passive decoration. It interacts with the solar wind itself, with the Sun's sprawling magnetic field lines, and with transient electromagnetic structures in ways that could create feedback loops. In theory, disturbances in the solar magnetic web could propagate back toward the star, nudging regions already unstable toward violent release. Now imagine this encounter aligning with the peak of the Sun's natural cycle, a time when magnetic fields are twisted, tangled, and poised for eruption. Atlas's ion tail could provide the spark at precisely the wrong moment, unleashing an energetic particle storm on a scale humanity has never witnessed. The Carrington event of 1859, triggered by a relatively modest coronal mass ejection, was sufficient to cripple telegraph systems across continents and to ignite auroras as far south as the Caribbean. That storm unfolded in a world largely free of dependence on electrical infrastructure. Were it to occur today, global networks would fracture, power grids would collapse, satellites would tumble into silence, communication systems would dissolve. Recovery would be counted not in weeks but in years, and the cost would be measured in trillions. An Atlas-amplified storm could eclipse even this nightmare. Charged particles racing at fractions of light speed would bombard Earth, carrying energies too great for shielding systems to absorb. Satellites designed with hardened electronics could fail en masse. Transformers on terrestrial grids might burn despite protective relays. Even the guardians that track space weather, the Solar and Heliospheric Observatory, the geostationary operational environmental satellites, and the Deep Space Climate Observatory could be crippled by the very storm they were designed to monitor. If these early sentinels were blinded, the waves of destruction would arrive without warning. The cascade would ripple through modern civilization with terrifying speed. GPS networks would collapse as satellites lost their precise timing signals. The backbone of the internet, dependent on synchronized data protocols, would splinter into chaos. Air traffic control systems, stripped of radar and navigation, would revert to visual rules across congested skies. Communications between continents could vanish, leaving nations isolated in the midst of crisis. The devastation would not be limited to Earth. Mars, already threatened by Atlas's direct approach, would face additional punishment. Its fragile atmosphere, barely clinging to the planet, could be stripped further by the torrent of charged particles. Surface radiation levels would spike to extremes, turning the dream of human settlement into an even more distant aspiration. The vision is stark, a cometary visitor amplifying the fury of the sun, converting ordinary space weather into a cosmic catastrophe. Atlas does not need to strike a planet to leave devastation in its wake. Its passage could entwine with the rhythms of our star, pushing solar storms beyond anything our species has endured, rewriting the conditions of life and technology across every world that orbits this fragile star. Radiation levels on the Martian surface would surge to values instantly lethal for any human explorers unlucky enough to be present. Even the great magnetic shields of Jupiter and Saturn, normally capable of deflecting the sun's tempests, could falter. Their moons Europa and Enceladus, long considered among the most promising places to search for extraterrestrial life, might endure doses of radiation so severe that their icy shells become sterilized to depths of meters. Subsurface oceans that once seemed sheltered could find themselves bombarded with energy sufficient to unravel fragile biochemical processes before they had any chance to thrive. The darkest prospect is that an Atlas-driven solar storm might not end when the comet retreats into the outer system. Disruptions to the sun's magnetic field can require months, even years, to regain equilibrium. During that unstable interval, the star might continue to release enhanced particle emissions, prolonging the threat to technological civilization across every orbit it touches. Humanity has no precedent for managing such a crisis. The historical record offers hints, ice cores that reveal spikes in cosmogenic isotopes, tree rings marked by sudden surges in solar activity, but these archives do not explain mechanisms or timelines. They whisper that such events have happened before, but they cannot tell us how an interstellar trigger might transform the pattern. Our space weather models, as sophisticated as they are, were never designed to accommodate variables introduced by alien comets tangling with the solar magnetic web. Forecasts we rely on could fail entirely, leaving decision-makers blind in the face of a storm unlike any seen in the space age. The policy questions are staggering. How do you protect a civilization when the phenomenon you are preparing for might arrive with almost no warning and persist for months? How do emergency services continue when their own communication systems are likely to be among the first casualties? How do you prevent social disintegration when supply chains built on GPS navigation, digital timing, and electronic payment systems falter simultaneously? The answer, in theory, lies in international cooperation. Yet the very electromagnetic chaos that threatens satellites and networks could also sever the communications needed to coordinate a global response. Imagine a planetary emergency unfolding while the cables, satellites, and data links required for cooperation fall silent. Nations might be reduced to isolated actors, struggling to manage a crisis whose scope no single country could possibly contain. But perhaps the most unsettling thought is that Atlas's influence may extend beyond electromagnetic storms and bursts of radiation. What if the comet leaves behind a chemical legacy, altering planetary atmospheres and environments in subtle ways? These changes might not announce themselves with dramatic auroras or electrical failures. Instead, they could accumulate quietly, decade by decade, reshaping planetary habitability and leaving a mark not of immediate destruction, but of long-term transformation. The true danger of Atlas may lie not in spectacle, but in the slow rewriting of the conditions for life itself. Part 9. Terraforming by disaster. The dream of terraforming Mars, transforming the red planet into a home for humankind, has inspired scientists and storytellers alike for generations. Most proposals describe a slow, carefully managed process, stretching across centuries. The deliberate release of greenhouse gases to thicken the air, the melting of polar caps to form seas and lakes, the introduction of hardy microorganisms to spark the first fragile ecological cycles. But what if 3i Atlas delivers its own brand of terraforming, not by intention, but by cosmic accident? And what if this transformation does not render Mars more hospitable, but drives it further into a hostile wilderness, less suited to life than ever before? The scale of Atlas's emissions is staggering. Spectroscopic studies reveal that the comet's coma is venting carbon dioxide at levels dwarfing anything previously measured in our solar system. Most of this gas will drift harmlessly into space, but even a tiny fraction captured by Mars would still amount to millions of tons of additional greenhouse gases introduced almost overnight. On the surface, this might seem like a shortcut to humanity's long-term ambitions. Carbon dioxide is the very gas most terraforming proposals count on to thicken Mars's thin atmosphere and trap more heat. Atlas might appear to be handing us a head start, but the reality is far more dangerous. Mars's climate is balanced on a knife's edge. Its fragile atmosphere has existed in relative equilibrium for millions of years. Terraforming plans assume careful, incremental additions, with engineers adjusting inputs to avoid runaway feedback loops. Atlas offers nothing so orderly. Its carbon dioxide arrives as a chaotic surge, unleashed alongside electromagnetic storms, potential impacts, and the seeding of alien dust across the planet. The mixture could destabilize Mars's atmospheric chemistry in ways no model has anticipated. Consider surface reflectivity, or albedo. Mars' ruddy deserts reflect sunlight in a pattern that helps preserve current temperature ranges. But Atlas may deposit thick layers of dark, organic-rich dust, material forged in a distant star system with unknown optical properties. Darkened ground absorbs heat more efficiently. A shift in albedo across wide regions could trigger localized heating strong enough to vaporize buried water ice. That new water vapor would inject another greenhouse agent into the air, amplifying warming. Combined with Atlas's carbon dioxide, it could drive atmospheric chemistry toward acidic precipitation, altering the surface environment in corrosive ways. The nightmare deepens when we consider the specter of Venus. That world, nearly Earth's twin in size, was transformed by runaway greenhouse heating into a hellscape of crushing pressure and searing heat. Mars's distance from the Sun and its weaker gravity would normally prevent such a fate. Yet Atlas introduces factors absent from natural planetary evolution. Exotic organics, delivered from interstellar space, might catalyze reactions that supercharge greenhouse warming, far beyond what carbon dioxide alone would produce. The timeline for such a shift could compress from geological epochs into human decades. Atmospheres under stress can cross invisible thresholds, after which change becomes unstoppable. What begins as a modest warming trend could accelerate into a rapid and irreversible transformation. Within years, Mars could transition into an alien climate that no spacecraft, no rover, and no habitat was designed to withstand. The consequences for exploration would be profound. Future missions rely on predictable Martian conditions. Life support systems are engineered for today's atmospheric composition, not for a chemically altered sky. A habitat that expects to recycle air through standard processes might instead generate toxins, turning protective shelters into death traps. Equally threatened is the principle of in situ resource utilization, the key to sustainable colonization. The promise of Mars has always rested on extracting water, oxygen, and fuel from local resources rather than shipping everything from Earth. But if Atlas reshapes the chemical inventory of the planet, those systems may fail. Machines intended to draw oxygen from carbon dioxide might yield corrosive byproducts. Water extracted from soil or ice could contain contaminants that clog systems or poison crews. Astronauts arriving in the 2030 seconds might find not a frontier ready for settlement, but a chemically hostile world where their equipment betrays them. The irony is stark. Humanity's great ambition has been to shape Mars deliberately, bending it toward habitability with patient engineering. Atlas could achieve the same goal in reverse terraforming Mars into a world forever lost to human hands. Water extraction systems, long envisioned as the lifeline of future Martian colonies, might face contamination from alien organics introduced by Atlas. Even the most advanced purification technologies could struggle, leaving the recovered water unsafe for human use. The psychological blow to humanity's colonization dream would be immense. Mars has stood as our nearest, most plausible refuge, a planetary insurance policy against crises that could one day overwhelm Earth. To discover that a wandering interstellar body had corrupted that possibility, just as our technology matures enough to plant roots there, would feel like watching the prospects of long-term survival vanish before our eyes. Yet the dangers Atlas brings may not stop with atmosphere and soil. Its influence could extend into Mars' electromagnetic environment, reshaping phenomena from auroras to dust storms. Mars's magnetic field is a faint echo of Earth's, offering little protection against charged particles. Any disturbance in the local space weather environment could leave the planet acutely vulnerable. A surge of electromagnetic activity might disrupt the ionosphere for decades, compromising radio communication systems on which exploration depends. Windows of reliable contact so essential for mission planning could become unpredictable, forcing engineers to reinvent communication technologies from the ground up. Dust storms present an even graver challenge. If Atlas's disturbances amplify their frequency or intensity, the planet's solar-powered infrastructure could be rendered unreliable. Panels already struggle under Martian dust. In a world of perpetual storms, they might be useless. Nuclear power, once considered an optional supplement, could become the only viable foundation for long-term operations. What unsettles planetary scientists most is the timeline of discovery. Atmospheric chemistry evolves slowly. Reactions triggered by Atlas could continue long after the comet's departure, altering the Martian environment in ways invisible to early instruments. It may take decades before the full consequences are recognized, leaving future missions stranded in a reality that no model predicted. This scenario underscores a humbling truth. Humanity's grasp of planetary atmospheres remains rudimentary. Our models perform reasonably well when charting slow geological transformations, but they falter when confronted with sudden large-scale chemical shocks, events like those Atlas could deliver without warning. And perhaps the most insidious danger lies not in physical transformation, but in perception. Imagine October 3rd unfolding quietly, just as official models predict no cataclysm, no electromagnetic storm, no chemical upheaval. Yet the public, primed for spectacle, refuses to believe it. The true disaster could arrive not through physics, but through fractured trust and the corrosive spread of misinformation. Part 10. The Don't Look Up Angle. In the modern era, information moves with a turbulence of its own, often more erratic than orbital mechanics and more dangerous than cosmic radiation. When astronomical events capture global attention, the gap between scientific reality and public perception can widen into a gulf where rational discourse is quickly lost. The October 3rd encounter between 3I Atlas and Mars presents nearly ideal conditions for such an informational catastrophe. The timing alone is problematic. The event coincides with solar conjunction, when Earth-based telescopes are poorly positioned to watch Mars, leaving scientists temporarily blind. The data that is gathered will demand weeks or months of painstaking analysis before definitive conclusions can be drawn. Worse still, the subject of that analysis is no ordinary comet, but an interstellar wanderer, a body whose behavior defies established patterns and whose anomalies invite speculation more readily than they yield firm answers. NASA and the European Space Agency have spoken carefully about Atlas, acknowledging its strangeness, outlining observation plans, but deliberately avoiding sensational language. Their restraint is scientifically responsible, yet it creates a void, and voids, in the information age, never remain empty. Social media platforms, governed by algorithms, tuned to amplify what is alarming rather than what is accurate, quickly fill that vacuum. By the time peer-reviewed studies emerge, the narrative may already be dominated by misinformation so deeply entrenched that corrections bounce off without effect. The precedent is not encouraging. The 2021 disclosures about unidentified aerial phenomena in the United States demonstrated how transparency efforts can backfire. Congressional hearings intended to clarify only deepened suspicion, fueling conspiracy theories rather than extinguishing them. Atlas represents an even greater challenge because the anomalies are real. Its immense carbon dioxide coma, wild brightness fluctuations, and unorthodox orbit offer just enough genuine mystery to make the most outlandish claims appear plausible to the untrained eye. The delayed release of hard data compounds the danger. The James Webb Space Telescope observed Atlas in infrared months before the encounter, but results must pass through rigorous peer review before being published. That process, essential for scientific integrity, may leave a vacuum of authoritative information for months. In the meantime, amateur astronomers and citizen scientists flood social media with their own images, often striking, but lacking the calibration and sensitivity of professional instruments. Artifacts that experts would dismiss as noise may appear convincing to audiences already primed for cosmic drama. This is the essence of the "don't look up" scenario. Even if October 3rd passes quietly, perhaps producing nothing more dramatic than subtle disturbances in Mars's electromagnetic environment, public perception could veer wildly. Mars orbiters might continue their work without incident, though some enter safe mode briefly as a precaution. Rovers on the surface might experience momentary communications dropouts, easily explained by ionospheric fluctuations. To scientists, such outcomes would be fascinating but far from catastrophic. To the public, however, the temporary blackout of images from Mars could look like deliberate concealment. Technical explanations, discussions of propagation delays, sensor recalibration, or spacecraft safe mode protocols sound like bureaucratic jargon to audiences hungry for spectacle. Social media narratives grow more elaborate, painting tales of cover-ups, hidden disasters, or suppressed discoveries. Within hours, millions might be convinced that something monumental happened at Mars, regardless of the truth. Atlas, anomalous and misunderstood, could end up not only reshaping our science, but also destabilizing our collective trust in the very institutions designed to reveal it. Computer-generated images claiming to show fresh Martian impact craters begin to circulate across social networks faster than space agencies can issue corrections. Amateur radio operators announce that they have intercepted mysterious transmissions from Mars orbiters' messages. They insist that NASA and the European Space Agency refuse to acknowledge. Cognitive scientists understand the psychological mechanisms at work. When people are primed for spectacle, silence is read as concealment, and cautious language sounds like evasion. When explanations involve technical details requiring specialized knowledge, they are interpreted not as clarity, but as deliberate obfuscation. The precedent is uncomfortably recent. The 2024 presidential election revealed how quickly misinformation can overwrite reality. Despite overwhelming evidence, unfounded claims about electoral fraud persisted, reinforced by repetition and confirmation bias. The very same dynamics could drive belief in cosmic cover-ups, with astronomical data treated as manipulated evidence in a grand deception. Oversight mechanisms meant to inspire trust might instead magnify confusion. Congressional hearings, intended to enforce accountability, could spotlight dramatic but uninformed testimony. Representatives lacking scientific training might demand absolute answers to questions that no dataset can yet resolve. Media coverage would seize on sound bites, elevating speculation into apparent fact. What began as uncertainty could snowball into a narrative of hidden disaster. International differences would add fuel to the fire. The European Space Agency, constrained by its own communication protocols, might release findings on a schedule out of step with NASA. Timing discrepancies would be portrayed as evidence of collusion or secrecy rather than routine procedure. Amateur astronomers in countries with varying traditions of transparency might publish observations that contradict official announcements. Chinese or Russian space agencies, shaped by different political imperatives, could characterize events in ways that appear inconsistent with Western interpretations. In the cacophony of competing accounts, accuracy would be just one factor among many determining which story gains traction. The most insidious risk lies in the cycle of premature disclosure. Under intense public and political pressure, space agencies might feel compelled to release tentative conclusions before the analysis is complete. Later corrections, the normal course of scientific self-correction, would then be framed as incompetence, or worse, deliberate deception. The familiar rhythm of misinformation would take hold. Initial sensational claims amplified, careful revisions ignored, and conspiracy theories hardened into unshakable belief. The damage to public trust could be profound. Agencies that earned credibility through decades of exploration, from Viking to Voyager, from Hubble to Perseverance, might find their authority undermined by a single episode of mismanaged communication. Future missions could launch into a public sphere already conditioned to doubt every official explanation. The real danger of the "don't look up" scenario is not that Atlas strikes Mars or unleashes chaos, but that its story is hijacked by the narratives humanity tells itself. And the cruelest irony is this: October 3rd might pass quietly. Atlas could sweep by with only subtle effects, no great impacts, no dazzling electromagnetic storms, no apocalyptic chemical transformations. What then? What happens when the most extraordinary astronomical encounter of our generation ends not with answers, but with deeper mysteries, leaving human psychology grasping for closure the universe never promised to provide? Part 11. If Mars takes the hit October 3rd, 2025. The day Mars died. Not in the way living things perish, no last breath, no silent fading into night, but in the sense that the planet humanity had imagined as our second home was irrevocably transformed. On this day, Mars ceased to exist as the beacon it had been for generations, its promise consumed by a single act of interstellar violence. At 1,400 hours Universal Time, Atlas Fragment Designation AF7 struck the planet's northern hemisphere with a fury that dwarfed human comprehension. 400 meters wide, forged of exotic ices and unfamiliar organics carried across interstellar gulfs, the fragment hit with energies equivalent to thousands of nuclear weapons. Bullets crawl compared to the velocity at which AF7 met the Martian surface. The Mars Reconnaissance Orbiter captured the unfolding cataclysm, a fireball brighter than the sun blazing against Mars's pale sky, followed by a shockwave racing outward at hypersonic speeds, flattening everything in its path. When the dust eventually thinned, a scar 37 kilometers across revealed itself, exposing rock that had lain buried since Mars was young. But the crater was not the end. It was the beginning of the planet's transformation into something alien. The impact had ripped millions of tons of frozen water from the crust, vaporizing ancient permafrost in seconds. The sudden flood of water vapor into the fragile Martian air-triggered weather systems no climatologist had ever modeled. Storms of unprecedented size and violence began forming within hours, reshaping atmospheric circulation in ways no precedent could predict. The electromagnetic pulse from the collision struck next. Every spacecraft orbiting Mars, MRO, Maven, Mars Express, the Trace Gas Orbiter was overwhelmed. Star trackers lost the heavens, communications drowned in static, and emergency safe mode systems activated across the fleet. But safe mode assumes brief turbulence, not the wholesale alteration of a planet's electromagnetic environment. One by one, as backup systems drained and hardware failed under stress they had never been designed to endure, the orbiters fell silent. For 14 months, there was only silence. Earth's connection to Mars, maintained unbroken for decades, was gone. The Perseverance rover, Curiosity, and an international flotilla of landers all vanished into static. At JPL, mission controllers stared at empty screens, stripped of the daily signals that had been their lifeline to another world. The psychological shock on Earth was immediate. Mars had represented humanity's next chapter, the story of our becoming a multiplanetary species. To watch it vanish was like witnessing our future collapse in real time. Stock markets reeled, aerospace industries bled contracts, and congressional panels demanded explanations that no one could provide. When communication was finally re-established through emergency relays and hastily launched replacements, the Mars that answered was unrecognizable. The entire climate engine of the planet had shifted. Seasonal dust storms, once predictable phenomena, had been replaced by chaos. Global storms raged with relentless frequency, choking the surface in a permanent shroud. Sunlight struggled through the suspended particles, rendering solar power unreliable and plunging surface operations into darkness. The new atmosphere reflected more sunlight than it absorbed, driving surface temperatures downward. A nuclear winter gripped Mars, lasting for more than 3 Martian years, reshaping it into a world colder, darker, and more hostile than any seen before. Radiation levels, too, had changed forever. The impact had dredged up radioactive material from deep within the crust, lofting it into the sky. A temporary ring of debris formed around the planet, a chaotic wreath of shattered rock that bombarded the upper atmosphere for months. The result was a carnival of auroras, brilliant yet ominous, paired with ionospheric chaos that rendered radio signals unstable for years. Phobos, the inner moon of Mars, was struck by collateral violence, already doomed to spiral into the planet over tens of millions of years. Its death was accelerated in an instant. Impact ejector slammed into its fragile body, destabilizing its orbit and forcing fragmentation to begin immediately. The moon broke apart piece by piece, scattering shards into orbit and creating a lethal debris field that would haunt Mars for centuries. The red planet we had studied, dreamed of, and prepared to colonize no longer existed. In its place was a world remade by catastrophe, a graveyard of human ambition, a warning carved in stone and dust. The fragments of Phobos did not scatter into orderly belts or graceful rings. They tore loose in every direction, boulders the size of buses and shards the size of skyscrapers, each following its own chaotic path through Mars's orbital corridor. To approach Mars after the catastrophe was to gamble with annihilation. Any spacecraft daring to enter its orbital space would be forced to navigate a 3-dimensional minefield of rocky fragments, moving at speeds where even a pebble could obliterate a billion-dollar mission. Mars had become a roulette table of cosmic violence, where the house always won. The dream of Mars colonization, so close to tangible reality in the early 2020s, dissolved in radioactive dust clouds that never cleared. The carefully orchestrated Artemis Mars missions, once slated to carry humans to the Red Planet, were cancelled indefinitely. International treaties that had painstakingly outlined the rules for exploration and settlement became irrelevant overnight. There was no longer a planet to govern, only a cosmic graveyard too hazardous for visitation. Private space ventures collapsed under the weight of this new reality. SpaceX's Starship, engineered with Mars cargo runs as its core mission, was hastily retooled for lunar outposts and asteroid mining operations. Blue Origin's Mars lander prototypes, years in development, were relegated to museum exhibits before ever touching Martian soil. Investors who had poured fortunes into Mars transport infrastructure watched their assets become obsolete in a single impact. For scientists, the sense of loss cut even deeper. Mars had been humanity's natural laboratory, a time capsule of planetary evolution, a stage where questions of climate change and potential extraterrestrial biology might finally be answered. Decades of rovers and landers had sifted its soils, sampled its rocks, and peered into its thin atmosphere. Now those machines lay buried beneath meters of irradiated ejecta, their discoveries silenced in an instant. What hurt most was knowing that Mars itself, as it had existed for billions of years, was gone on a timescale meaningful to human civilization. Planetary recovery is measured in eons, Atmospheres can rebuild, chemistry can stabilize, but the process unfolds across millions of years. The Mars that might one day emerge from Atlas's chaos would not be the Mars humanity had studied, dreamed of, and prepared to colonize. Even the tilt of its axis had shifted, altering the rhythm of its seasons. The sudden infusion of water vapor and exotic organics from the interstellar fragment triggered atmospheric chemistry unlike anything in terrestrial models. This was not controlled terraforming. It was violent, runaway transformation, stripping away centuries of planning in a single day. The ripple effects spread across the solar system. Mars had been humanity's stepping stone, the natural base for deeper exploration. Its loss forced a wholesale recalculation. Without Mars as staging ground, reaching the asteroid belt or the Jovian moons became vastly more complex and expensive. Ambitions of interplanetary expansion were delayed by decades, perhaps centuries. Psychologically, the trauma reshaped a generation of scientists, engineers, and dreamers. Where comets had once inspired awe with their glowing tails, they were now regarded with suspicion. The universe, once imagined as a stage for human destiny, revealed itself as an indifferent arena where chance encounters could erase entire futures. Governments responded with urgency. Planetary defense programs, long the province of modest budgets and academic interest, became central to global security. The DART mission, once dismissed as a symbolic demonstration, was reinterpreted as a proof of concept for survival. Funding surged into programs designed to detect, track, and if necessary, deflect incoming bodies. Humanity had learned the cost of ignoring cosmic threats, yet the most unsettling revelation was existential. If Atlas by accident could annihilate Mars as a destination, then what of other interstellar wanderers moving silently through the void? How many more fragments, forged in alien star systems, might be crossing the solar system on unpredictable trajectories? Monitoring systems originally designed for near-Earth asteroids were expanded, their scope widened to interstellar objects. The comforting fiction of a mostly empty universe was gone. Space, humanity finally understood, was crowded with hazards capable of rewriting planetary histories in a single encounter. And still, a paradox lingered. As devastating as the imagined destruction of Mars might be, reality often resists neat endings. The cosmos rarely delivers cinematic closure. What if Atlas's October 3rd encounter passes with no great impact, no shattering of moons, no dramatic scars across the red planet? What if instead of answers, humanity receives only ambiguity, small anomalies, subtle electromagnetic disturbances, faint traces of organic chemistry, leaving us with more questions than clarity? Perhaps that is the true legacy of Atlas, not a single disaster that killed Mars in one day, but the unsettling recognition that our solar system lives at the mercy of cosmic chance, and that the line between catastrophe and mystery is thinner than we dare to admit. Part 12. If Mars Survives. October 3rd came and went not with a scream, but with a whisper. The European Space Agency's final trajectory update, released with clinical precision, placed Atlas at its closest approach to Mars, 30.2 million kilometers, at exactly 11:17 Universal Time. No fragments slammed into the planet's surface. No electromagnetic storms lit up its thin skies. No global dust tempests rose to smother the red planet in radioactive haze. Mars continued its orbit around the Sun, ancient and unchanged, apparently unmoved by its brush with the interstellar visitor. The first official communiqué arrived 6 hours later from ESA Mission Control. 3I divided by Atlas has completed its Mars encounter within all predicted parameters. Mars orbital assets report normal operations. No anomalous activity detected at this time. Further analysis pending. 42 words. efficient, accurate, antiseptic. They managed to sound both reassuring and profoundly unsatisfying. Within minutes, social media erupted. The collective mood was not relief but indignation. "That's it?" became the #1 trending phrase on Twitter. Reddit forums that had spent months in fevered speculation dissolved into bitter arguments about whether this anticlimax proved scientific competence or confirmed the existence of a coordinated cover-up. The reaction revealed something fundamental about human psychology and our expectations of the cosmos. For months, Atlas had held the world in thrall precisely because it represented uncertainty. Its interstellar origins, erratic outbursts, and exotic chemistry fed speculation that stretched from sober academic papers to outlandish theories about alien technology. The one thing all these narratives shared was the assumption that October 3rd would deliver something spectacular: impact, chaos, or revelation. But the universe does not write for human narrative satisfaction. It operates under physical laws indifferent to drama. Astronomical events, even profound ones, often manifest not as spectacle but as subtle variations, detectable only to instruments designed to see beyond the human eye. NASA's own statement, released 12 hours after closest approach, embodied this reality. Preliminary analysis of Mars orbital data indicates minor variations in ionospheric density, consistent with expected interactions between Atlas's ion tail and Mars's magnetosphere. No structural damage to orbital assets detected. Surface operations continuing nominally. The words were precise, professional, technically significant, and utterly devoid of the cosmic fireworks the public had been primed to expect. Where were the images of Atlas blazing like a dagger of light across Mars's skies? Where were the auroral storms visible even to Earth-based telescopes? Where were the obvious scars, the indelible marks of history? The truth was harsher. Most of the dramatic effects that scientists anticipated were invisible to ordinary observers. Variations in ionospheric density do not paint the sky. Magnetosphere interactions create data traces, not cinematic auroras. The real science was happening in the numbers, in the subtle graphs, in months of analysis yet to come. Professional astronomers understood this. They knew the true significance of the October 3rd encounter might not become clear for months or even years. Tiny gravitational nudges, trace chemical shifts in Mars's atmosphere, long-term perturbations in electromagnetic conditions. These were the details that would matter, but they required patience, data integrity, and rigorous analysis. The public, however, was not built for patience. Media ecosystems thrive on immediacy. Attention spans are dictated by news cycles, not orbital mechanics. Atlas's story, which had thrived for months on mystery and anticipation, lost its momentum the moment it failed to deliver cinematic spectacle. Into that vacuum rushed conspiracy. Why were there so few images? Why had agencies been so secretive about observational plans? Why did every statement sound like technical camouflage? These questions metastasized across platforms primed to reward suspicion over nuance. Amateur astronomers, who had prepared elaborate observation campaigns, found themselves with nothing extraordinary to show. Their telescopes captured exactly what models had predicted: a comet passing near Mars, quietly, uneventfully. Ground-based observatories struggled with the same dilemma. Their spectroscopy revealed fascinating shifts in Atlas's emissions valuable for specialists, but meaningless to a general audience craving spectacle. Radio arrays documented subtle plasma variations in Mars's environment again, science, but not imagery. Algorithms did what algorithms always do. They elevated not the careful, cautious explanations of scientists, but the emotionally charged narratives of suspicion. Within days, computer-generated images of fictional Mars craters circulated faster than official corrections. Amateur radio enthusiasts claim to have intercepted panicked transmissions from orbiters, rumors of silent catastrophes, of data suppression, of secret cover-ups, spread faster than any official reassurance. The irony was inescapable. From a scientific standpoint, the October 3rd encounter was a triumph. Predictions had held, models had proved accurate, observational campaigns gathered pristine data on the behavior of an interstellar object in a planetary encounter. It was precisely the kind of success that builds confidence in planetary science. Yet from a public perception standpoint, it was a disaster. Expectations had been stoked to such extremes that only apocalypse would have satisfied them. In its absence, conspiracy filled the void. The cosmic whisper of October 3rd underscored a painful truth. Humanity does not merely observe the universe. We project our fears, our hopes, our hunger for drama onto it. When the cosmos refuses to perform to script, we invent our own narratives. Atlas had not destroyed Mars, nor reshaped the solar system, nor set the skies ablaze. Its legacy, at least in the short term, was to remind us that in the age of algorithms, perception can diverge so far from reality that the absence of catastrophe becomes its own kind of crisis. The careful, methodical approach that defines professional astronomy was misread by the wider public as deliberate obfuscation. Congressional representatives, many of whom had used Atlas as a rhetorical backdrop for speeches on planetary defense and space funding, suddenly found themselves stranded. They had promised their constituents cosmic revelation, only to be confronted with cosmic quiet. Hearings before the House Science Committee, initially framed as emergency sessions to address the Atlas crisis, were hastily rebranded as routine oversight briefings on NASA's Mars programs. What had been marketed as a confrontation with existential risk became a conversation about budget lines and project milestones. The media pivoted with equal speed. Cable networks that had built elaborate programming schedules around the October 3rd encounter were left scrambling for content to fill the void. Sets dressed with comic graphics and countdown clocks now looked faintly ridiculous. Panels of experts, assembled to speculate about interstellar catastrophes, found themselves explaining instead why the absence of drama was always the most probable outcome. Their scientific precision, the quiet reassurance that models had worked exactly as intended, did little to satisfy an audience that had been primed for spectacle. Within the scientific community, the mood was equally conflicted. Astronomers who had invested months into planning observation campaigns produced results that were technically remarkable. The most detailed spectra ever obtained of an interstellar visitor, high-resolution imaging from the James Webb Space Telescope, and coordinated multinational data collection that functioned with flawless efficiency. Yet these achievements failed to translate into public excitement. The very fact that catastrophe had been successfully predicted and avoided made the story less compelling than if predictions had been wrong. Success in planetary science is often invisible. Failure, by contrast, is dramatic. International cooperation, one of the brightest triumphs of the Atlas campaign, barely registered in public discourse. NASA, ESA, JAXA, and other agencies had synchronized their efforts to an unprecedented degree, ensuring that no contradictory statements confused the global audience. But in a media ecosystem that thrives on controversy, this smooth coordination proved almost self-defeating. The lack of drama was reframed as evidence of conspiracy rather than competence. Even the James Webb Space Telescope, whose instruments captured some of the sharpest images of an interstellar nucleus ever obtained, saw its triumph overshadowed. The subtle infrared signatures that revealed Atlas's exotic chemistry could not compete in the public imagination, with the phantom images of craters and fireballs that had filled speculative articles in the months before. The narrative had been built on catastrophe. Scientific nuance could not replace it. Amateur communities fared no better. Radio operators who had prepared elaborate monitoring setups to capture evidence of electromagnetic disruptions recorded nothing but routine spacecraft chatter. Their anticipation of history in the making collapsed into a logbook of normal operations. For many, it felt like the universe itself had reneged on a promise. Gradually, October 3rd transformed from an astronomical milestone into a cultural symbol. Social critics began to call it the Atlas anticlimax, an emblem of institutional failure to manage public expectations. Educators struggled in classrooms as students, who had followed the comet eagerly for months, lost interest when nothing spectacular occurred. Teachers who tried to emphasize the subtle but significant discoveries, variations in ionospheric density, traces of chemical anomalies in Atlas's coma, found themselves battling yawns and disappointment. The lesson seemed to be that only catastrophe could sustain attention. For space scientists, this was alarming. If the most dramatic interstellar visitor ever recorded could not hold public interest without explosions or apocalyptic imagery, what did that mean for the future of space exploration? Funding decisions, already precarious in many countries, depend on public fascination. Competing against terrestrial crises, climate change, pandemics, political upheaval, astronomers realized that a comet behaving too well might ironically weaken their case for long-term investment. Most troubling of all was the speed of collective forgetting. Within weeks, Atlas slipped almost entirely from mainstream headlines. What had once dominated every science feed, every late-night monologue, every speculative YouTube video, now vanished into silence. The data analysis continued, of course, in laboratories and observatories across the world, but outside those circles the comet's story seemed finished. Yet the silence was deceptive. Astronomers knew that the true implications of Atlas's passage could take months, even years, to fully unfold. Gravitational perturbations accumulate invisibly. Subtle chemical traces in Mars's atmosphere may not reveal their consequences until decades of climate cycles have passed. Plasma interactions with the solar wind may ripple outward in ways that even the most advanced models struggle to predict. The anticlimax was not necessarily an ending. It could have been a beginning, a quiet prelude to larger consequences hidden behind the deceptive calm of October 3rd. While the world moved on, distracted by politics and entertainment, a handful of scientists whispered a darker question in conference corridors. What if Atlas's true story had only just begun? Part 13: Atlas as the Messenger. Throughout human history, comets have been treated as punctuation marks in the great manuscript of civilization, fiery commas, and exclamation points that interrupt the familiar rhythm of the heavens. They were interpreted as omens of change, celestial messengers whose meaning demanded careful interpretation by priest astronomers, gazing upward from their temples and observatories. To ancient cultures, the sudden arrival of a comet was a divine communique, a warning or promise etched across the night sky. Atlas enters our solar system bearing credentials that set it apart from every comet ever recorded. It is not one of our sun's well-known wanderers, bound to elliptical orbits that can be charted years in advance. This is something wholly alien, a true interstellar emissary, traveling across distances so immense that its icy nucleus may preserve the chemical memory of stars long extinguished. Stellar systems that vanished before Earth's continents assumed the shapes we recognize today. The message Atlas carries is not written in words, but in the deep language of matter itself, in atomic structures, molecular bonds, isotopic ratios, and crystalline lattices forged under conditions that have never existed within our solar system. Each spectrographic analysis of its streaming emissions tells a fragment of a story, of alien stellar winds sculpting matter at unfamiliar intensities, of radiation environments at energies our star has never produced, of gravitational pressures operating at the edges of known physics. In its chemistry, Atlas is a fossil, a time capsule, and perhaps something more. What if the comet's message transcends simple composition? What if its erratic brightness, its strangely geometric coma, and its torrential outpouring of carbon dioxide are not random quirks of ice sublimation but something more structured? What if Atlas itself is a slow-motion broadcast, an engineered signal written in cometary form? Imagine a civilization so advanced it had mastered the mechanics of celestial engineering. To such beings, comets could serve as couriers, carrying both material and information across interstellar gulfs. Controlled gas emissions might function as the equivalent of beacons, visible across light years, designed to ensure that any technological species capable of building spectroscopes would notice and study the visitor. The mathematics of such communication would be as elegant as it is universal. Binary patterns could be inscribed in brightness variations, sequences of flare and dimming that follow rhythms no natural process could sustain by chance. Spectral lines could be subtly modulated, embedding structured information in ratios of emission intensities, detectable only by advanced analysis. Even the trajectory itself could become part of the message. Small, deliberate adjustments in course during its approach could trace geometric figures against the star field patterns that no natural comet could ever create. Seen through this speculative lens, Atlas's behavior acquires a startling new dimension. Its enormous carbon dioxide coma, orders of magnitude greater than any comet in our records, might not be an anomaly at all, but a deliberate amplification, a method of broadcasting its presence to anyone watching. The erratic brightness surges that baffle astronomers could conceal structured pulses, signals waiting for decoding. Its timing arriving now, when humanity has finally developed the observational power to probe such an object in detail, might be more than coincidence. If Atlas departed its home system thousands of years ago, its designers might have calculated a trajectory that would intersect our solar system precisely when our species had reached the threshold of interplanetary technology. For the first time in history, we have the instruments capable of reading such a message, if it exists. Consider the James Webb Space Telescope, humanity's most sophisticated eye on the cosmos. Its infrared spectrometers are capable of dissecting the faintest molecular fingerprints in a comet's coma. Atlas's arrival so soon after Webb's deployment creates conditions almost suspiciously ideal. A revolutionary observatory paired with an interstellar visitor unlike any we have ever seen. The European Space Agency's coordinated observation campaign has multiplied this advantage, assembling an unprecedented multinational dataset. Within those terabytes of emission spectra, orbital telemetry, and photometric records may lie patterns invisible to the naked eye, patterns only machine learning algorithms, trained on vast datasets, can hope to extract. If this is indeed a message, decoding it requires abandoning every anthropocentric assumption about communication. We cannot expect spoken language, binary computer code, or even mathematics expressed in human notation. An alien civilization might use the very physics of sublimation as its alphabet, designing emission geometries and spectral anomalies as their form of cosmic script. What to us looks like chaos could be, in fact, deliberate structure. The implications are staggering. If Atlas carries an embedded signal, then humanity stands on the brink of becoming not just explorers of interstellar objects, but recipients of interstellar communication. For the first time in our species' history, the question would not be whether we are alone, but whether we have the intelligence and the humility to recognize a message written in the language of the stars themselves. The signals, if they exist, would not resemble words or pictures, but mathematics, the one true language of the cosmos. Patterns of prime numbers could be hidden within Atlas's flickering brightness, rhythms that nature rarely produces by accident. Geometric constants might be embedded in the ratios of spectral lines, whispering of pi or phi across interstellar space. Even isotopic compositions, sculpted by artificial processes, could carry physical constants that stand out against the background noise of natural chemistry. The real challenge lies in discerning the difference between nature's strangeness and genuine design, a task that pushes the limits of our still young analytical techniques. Interstellar objects are anomalies by definition, formed under alien suns. Their chemistry and structure reflect stellar nurseries unlike our own. Their erratic behaviors, brightness surges, peculiar coma geometries, unusual emission signatures already stretch the boundaries of our models. How, then, do we decide which deviations are merely exotic and which are intentional? Astronomers face the possibility that the very behaviors they might dismiss as quirks could be the lines of a message written in cosmic ink. Amid this uncertainty, amateur astronomers and citizen scientists have stepped forward. Free from the scheduling constraints of professional observatories, they can watch Atlas night after night, creating continuous data streams that complement professional snapshots. If embedded signals exist, they may reveal themselves most clearly in these long-term records, where patterns emerge from persistence rather than isolated glimpses. The search for extraterrestrial intelligence has begun taking this prospect seriously. The SETI Institute, long known for scanning radio frequencies, has quietly applied its signal analysis algorithms to the Atlas datasets. Their methods, honed over decades of searching for narrowband radio beacons, are now being adapted to light curves, spectral signatures, and orbital dynamics. No announcements have been made, but the mere act of diverting such expertise speaks volumes. It suggests that among those most experienced in distinguishing noise from intention, the possibility of Atlas as a communications platform is not dismissed outright. And if the message exists, it may not be for us not yet. Interstellar communication unfolds on timescales measured in millennia. Any information sent across such gulfs would necessarily assume that recipients may not be ready to understand it immediately. Atlas might be delivering a lesson we can only grasp once. Our mathematics, physics, and philosophy have matured. It could be a cosmic library card, not the library itself, a seed of knowledge meant to germinate in civilizations that endure long enough to earn comprehension. The psychological shock of confirming such a message would dwarf any physical risks the comet poses. To discover we are not alone through the patient, deliberate arrival of interstellar information would force humanity to reframe its place in the galaxy. Our debates about planetary defense, colonization, and survival would pale beside the recognition that intelligence is not confined to Earth, and that communication across the stars is not only possible, but perhaps already underway. Yet absence is not proof of silence. The fact that no clear message has been found should not be mistaken as evidence that none exists. The most sophisticated communication may be buried in patterns that require tools not yet invented. Generations to come may look back at today's terabytes of Atlas data and marvel at how much meaning we overlooked, how much richness lay hidden in numbers we dismissed as noise. International collaboration offers a safeguard against parochial control. No single nation owns Atlas. Its trajectory belongs to every sky on Earth. The distributed nature of current campaigns, NASA, ESA, JAXA, amateur groups across continents, ensures that if a message is there, it will not be easily suppressed or monopolized. The decoding effort itself may be the first true test of whether our species can treat cosmic knowledge as a shared inheritance rather than a weapon or commodity. But perhaps Atlas's greatest revelation is not what it brings, but what it exposes in us. Within months, its presence became a mirror for our anxieties about secrecy, disaster, and truth. Social media algorithms amplified fear over evidence. Conspiracy theories outpaced careful analysis. The comet became less an astronomical body than a projection screen for human suspicion. Atlas, then, may already have delivered its message not in chemistry or light, but in the way we responded to its arrival. The October 3rd encounter has become something larger than an astronomical milestone. It stands as a mirror held up to our civilization, reflecting how we respond to the unknown, how much we trust expertise, and how fragile our ability remains to separate genuine mysteries from manufactured crises. The comet's passage reminds us that the most enduring lessons may not come from physical changes to Mars or any other planet, but from what the encounter reveals about ourselves. Perhaps the deepest realization is temporal. Our solar system is not an isolated haven but a crossroads in a galactic neighborhood where interstellar wanderers pass more often than history has recorded. Their rarity in our chronicles is an artifact of perspective. Human civilization has been technological for only a fleeting moment, a thin slice of astronomical time. Atlas may be the first of many such visitors we are now equipped to notice. If so, the frameworks we are constructing to study its scientific, institutional, and social could set precedents for how humanity will face an entirely new class of cosmic events. The datasets collected during this encounter will outlive the comet's brief sojourn through our skies. Spectroscopic fingerprints, orbital calculations, and emission profiles form the most detailed record of an interstellar object in human history. What we cannot interpret now may one day yield discoveries beyond today's imagination. Future researchers, armed with analytical tools not yet invented, could uncover patterns that escape us entirely. Some of Atlas's most significant secrets may not surface until the 2040 seconds or later, when theoretical frameworks have matured enough to decode signals hidden within data we already possess. The cooperative spirit surrounding Atlas has also been remarkable. NASA, ESA, JAXA, and countless universities and observatories have worked together with amateurs across the globe in an unprecedented choreography of shared observation. These protocols, data pipelines, coordination schedules, and open archives may become the model for future encounters with interstellar objects, or with cosmic phenomena that disregard national borders. In this sense, Atlas is as much a social experiment as it is a scientific one, but cooperation carries risk. A misinterpretation in one dataset, if unchallenged, can ripple across the entire collaborative network, embedding systematic error into global conclusions. The very strength of coordination, the ability to unify perspectives, can also become a weakness if it blinds the community to dissenting evidence. Distributed amateur observations provide a vital safeguard here, offering continuous coverage beyond the narrow windows of professional telescopes and ensuring that no single narrative can dominate unchecked. Future encounters with interstellar wanderers will demand a new kind of science campaigns that weave together the precision of professional observatories with the persistence and reach of amateur astronomers scattered across the globe. Atlas has already demonstrated the power of such coordination. University classrooms turned the comet into a living case study, a real-time experiment in cosmic unpredictability. Educational institutions built teaching modules, observation protocols, and data analysis exercises that transformed students into participants in one of the most ambitious astronomical investigations in history. These materials will outlast the comet's fleeting passage, shaping how the next generation of scientists approach not just interstellar objects, but cosmic mysteries of every kind. Yet Atlas's legacy may extend far beyond academia. Its psychological and cultural impact has been no less profound than its scientific one. By its very presence, this fragment of another star system shattered the illusion of cosmic isolation. Interstellar space no longer seems a void. It feels populated, not only by rocks and ice, but perhaps by distant civilizations whose artifacts might occasionally wander into our skies. Public opinion surveys conducted during the comet's approach revealed a measurable shift in attitudes towards space exploration, planetary defense, and international cooperation. A single cosmic visitor altered the trajectory of human imagination, perhaps for decades to come. The encounter also revealed how fragile our technological civilization truly is. Our spacecraft, satellites, and communication systems were engineered under the assumption that the cosmic environment between solar storms and asteroid impacts is relatively stable. Atlas introduced new uncertainties, debris streams that might linger for decades, electromagnetic anomalies we scarcely understand, chemical contamination that could alter planetary environments in subtle ways. Future missions will need to plan for these risks, developing hardware and protocols designed not just for the predictable hazards of our solar system, but for the unpredictable signatures of interstellar traffic. Legal and ethical frameworks are equally unprepared. The Outer Space Treaty and its successors were written with the expectation that exploration would involve familiar solar system bodies, planets, moons, and asteroids formed in our own stellar nursery. Atlas raised questions those documents never anticipated. What happens if an interstellar visitor carries embedded information, technological artifacts, or even biological material? Do such objects belong to the whole of humanity, or to the first nation or corporation to intercept them? What responsibilities do we bear to protect our worlds from contamination, while still pursuing the knowledge such objects might contain? These dilemmas demand new international agreements, balancing scientific opportunity with planetary safety, national security with transparency, curiosity with caution. The Atlas encounter, then, may be remembered as humanity's graduation ceremony, our first step from being a civilization confined to one star system into a species forced to reckon with galactic-scale phenomena. Whether we have passed or failed, this test will not be clear for decades. But the patterns we set now, the institutions we build, and the lessons we choose to heed will shape our cosmic trajectory for generations. As Atlas recedes toward the outer solar system and ultimately into interstellar night, it carries more than the exotic chemistry of a vanished stellar nursery. It also carries the light and radio signatures of a young technological species, etched into the electromagnetic spectrum by our telescopes, transmitters, and satellites. Future interstellar travelers, should they exist, may encounter these echoes and draw their own conclusions about whether humanity is ready to take its place among them. Perhaps October 3rd, 2025, will not be remembered as the day Mars trembled under threat, but as the day humanity confronted its own vulnerability and began to understand that interstellar messengers are not rare. They are the background rhythm of the galaxy, and each one is a test of our wisdom. The greatest danger Atlas poses may not be impact, electromagnetic chaos, or atmospheric change. The true catastrophe would be failing to learn from it, failing to recognize that our universe is stranger, more dynamic, and far more dangerous than we have ever allowed ourselves to believe. Part 14. Closing speculation. What if we are missing the real story? October 3rd has passed. Mars continues its ancient orbit around the Sun, indifferent to the dramas of human speculation. The spacecraft that monitor the red planet transmit their routine data as if nothing unusual has occurred. Atlas itself, once the focus of global fascination, recedes steadily toward the outer solar system, its closest approach now a matter of record rather than imminent anticipation. And yet, in the silence that follows, a more disquieting question arises. What if the narrative we constructed around Atlas of potential impacts, atmospheric disruption, electromagnetic storms, or chemical contamination was never the true story at all? Perhaps the real significance of Atlas lies not in its physical interaction with Mars, but in what its arrival has already revealed about us, our institutions, our information systems, our decision-making processes, and our collective ability or inability to separate genuine cosmic threats from manufactured crises. The clues for this interpretation are not hidden in spectroscopic data or orbital calculations. They lie instead in the strangely deliberate patterns of institutional behavior that have surrounded Atlas since its discovery. From the beginning, information about this interstellar visitor has been released with remarkable precision. Updates came not in the usual scatter of press conferences, research papers, and amateur findings, but in carefully coordinated increments. International space agencies that often compete for attention and funding spoke with one voice. The timing of data releases seemed designed not merely to inform, but to control the tempo of public attention. Consider the James Webb Space Telescope's August observations of Atlas. JWST represents the most advanced astronomical instrument ever deployed, capable of producing data that revolutionizes entire scientific fields in a single exposure. Yet months after those observations, no striking images, no headline-grabbing revelations have emerged. Instead, officials speak cautiously of analysis in progress and peer review underway. NASA's Science Mission Directorate, normally quick to frame its discoveries in inspirational terms, has limited itself to technical briefings, trajectory updates, density models, emission spectra, all delivered with clinical detachment. The European Space Agency, bound by different political constraints, has nonetheless mirrored NASA's reticence almost exactly. Such harmony in communication suggests coordination that transcends normal institutional rivalry. What we have not seen is equally telling. There were no dramatic public images of Atlas racing past Mars. No electromagnetic fireworks packaged for mass consumption. Instead, the encounter was framed as a technical success, but a visually unremarkable one. Was this simply the nature of the phenomenon, or was it the product of deliberate information management? Professional astronomers, who typically compete with almost ruthless intensity for first publication and media credit, have displayed an unusual level of collective discretion. Preliminary results that would once have appeared in rapid-release journals or at headline conference sessions are instead trickling out only after layers of institutional review. Even the amateur astronomy community, normally a vibrant chorus of independent voices, has remained curiously subdued. Atlas was well within the reach of advanced backyard equipment, yet independent analyses have been scarce, as though a quiet pressure to coordinate, rather than compete, has shaped even this distributed network. Meanwhile, political institutions appear to have taken Atlas far more seriously than their public postures suggest. Congressional oversight of NASA and related agencies has been conspicuously respectful, even deferential, in contrast to the usual practice of grilling administrators over budgets and schedules. Hearings that had been expected to spotlight Atlas were quietly folded into broader discussions of Mars exploration, leaving the impression that sensitive matters were being handled elsewhere, outside the public record. This raises the possibility that Atlas is being treated not merely as an astronomical curiosity, but as a matter of national security and international diplomacy. Current space law crafted in the Cold War era was designed to manage satellites, lunar missions, and near-Earth asteroids. It provides little guidance for dealing with an interstellar visitor whose chemical makeup, orbital characteristics, or even potential artificiality could have implications beyond science, implications for defense, technology, and geopolitics. If Atlas does carry knowledge too disruptive for unmediated release, embedded messages, exotic materials, or clues to technologies we cannot yet wield safely, then the silence, the delays, and the careful choreography may represent not deception, but stewardship. A managed disclosure, stretched over years or even decades, could be intended to prepare humanity gradually, calibrating each revelation to match our evolving capacity to absorb it. This scenario would explain the paradox at the heart of the Atlas story. The absence of spectacle was not the failure of observation, but the success of control. The images we did not see, the data still under lock, the caution of scientists and the restraint of politicians, all of it may point to a recognition that Atlas is more than comet, more than anomaly. It may be a messenger, or at least a mirror, forcing us to confront not the fragility of Mars, but the fragility of our own civilization's ability to respond to the unknown. If so, the October 3rd encounter will not be remembered for what happened at Mars, but for what it revealed on Earth. That our greatest vulnerability may not be physical destruction from the cosmos, but the way information about the cosmos can be managed, manipulated, or misunderstood. The current framing of Atlas, as an interesting but ultimately routine astronomical phenomenon, may represent only the opening phase of a much longer educational process. What appears to be simple scientific normalcy could in fact be the groundwork for something far larger, a carefully staged sequence designed to prepare humanity for eventual recognition of the object's true significance. Universities and scientific organizations may already be building curricula that will one day address questions of interstellar communication, cosmic citizenship, and the ethics of contact. But these themes cannot be introduced suddenly. They require gradual cultural acclimatization, political frameworks, and psychological resilience. In this interpretation, the present silence, the cautious language, and the lack of spectacle conceal preparation for extraordinary revelations yet to come. And yet, even this scenario rests on an assumption that Atlas carries meaning profound enough to justify managed disclosure. What if the most unsettling possibility is simpler? That Atlas is precisely what conventional astronomy insists: a routine interstellar body, shaped by natural laws, following predictable trajectories, carrying nothing more mysterious than the frozen chemistry of a long-dead star system. If so, the disturbing revelation is not about the comet, but about us. Our readiness to project hidden significance, to fill gaps in data with speculation, reveals dangerous vulnerabilities in the way our civilization processes information. The ease with which conspiracy theories and alternative narratives attach themselves to Atlas suggests that modern society has become dangerously susceptible to disinformation. A genuinely routine astronomical event, one that professional astronomers always expected to be scientifically interesting but visually unremarkable, was enough to trigger months of fear, speculation, and suspicion. If a comet can do this, what happens when humanity faces an actual cosmic threat, or receives a genuine interstellar message? Would we be capable of rational analysis under pressure, or would our institutions collapse into rumor, mistrust, and discord? Atlas may have functioned as an inadvertent stress test of our species' collective decision-making processes. The results are not reassuring. The October 3rd encounter thus becomes more than a data point in planetary science. It becomes a mirror held up to human civilization, reflecting our relationship with the unknown, our fragile trust in expertise, and our difficulty distinguishing between mysteries that demand patience and crises manufactured by information systems that reward drama over truth. In this sense, Atlas forces us to recognize that the greatest danger of cosmic encounters may not be physical destruction, but informational chaos. Perhaps the most profound realization is temporal. Our solar system does not exist in isolation, a lonely bubble drifting through sterile space. It lies within a galactic neighborhood where interstellar visitors are likely common, routine, even inevitable. The rarity of such encounters in human records reflects not cosmic scarcity, but the brevity of technological civilization relative to astronomical timescales. We have simply not been watching long enough. If Atlas is the first of many interstellar wanderers, our expanding detection capabilities will reveal in the coming decades. Then our current response, both scientific and social, may be setting the template for how humanity will address an entire class of future events. The frameworks we build today for analyzing Atlas, both in terms of technical procedures and social management, will shape our response to future visitors. The spectroscopic measurements, orbital models, and emission analyses gathered during this campaign represent the most comprehensive dataset ever assembled on an interstellar object. Long after Atlas itself has vanished into the dark beyond Neptune, its data will remain. Hidden within terabytes of readings may lie insights that only future technologies can unlock. Graduate students decades from now may discover patterns in today's numbers that reveal truths invisible to our current models. The most significant discoveries of Atlas may not emerge until the 2040 seconds or later, when science has caught up with the gift the comet left behind. International cooperation has been one of Atlas's quiet triumphs. Agencies across continents shared data and coordinated observations with a smoothness rarely seen in competitive scientific environments. This coordination may become the prototype for managing cosmic events that transcend national boundaries. But coordination carries risks as well. If current interpretations miss something crucial, if the data contain anomalies dismissed as noise, or patterns misread through consensus, those mistakes may be amplified globally, repeated across institutions, harder to identify and correct. The very structures that enable comprehensive analysis can also create systemic blind spots. Amateur astronomers have provided a vital counterbalance, their distributed networks capable of continuous monitoring in ways professional telescopes cannot match. Their role underscores an important lesson for the future. Interstellar visitors are best studied through campaigns that blend professional precision with amateur dedication and geographic reach. The Atlas experience has already seeded new protocols and teaching materials, ensuring that future scientists and citizen observers alike will approach the next cosmic visitor with stronger methods and clearer expectations. But the impacts of Atlas extend far beyond science. The psychological and cultural shock of confronting a confirmed interstellar traveler has forced humanity to reconsider its place in the universe. For centuries, interstellar space seemed abstract, distant, more the domain of philosophy and science fiction than of immediate human experience. Atlas changed that. Its mere existence, visible in telescopes across the globe, made interstellar space feel near, tangible, a highway that other objects, and perhaps other civilizations can and do traverse. Public opinion polls during Atlas's approach revealed striking shifts. Support for planetary defense programs rose. Interest in space exploration funding spiked. International cooperation, long an abstract ideal, suddenly seemed essential when faced with an object from outside the solar system. These shifts suggest that the cultural and political legacy of Atlas may endure longer than any physical effect it had on Mars or the inner planets. In the end, Atlas may be remembered not for what it did, but for what it revealed. It revealed our vulnerabilities to misinformation. It revealed the strengths and weaknesses of global scientific cooperation. It revealed the hunger of human beings to find meaning, even in silence. And above all, it revealed that our civilization now stands on the threshold of a new era, one where interstellar visitors are not curiosities, but recurring chapters in the ongoing story of our place in the cosmos. Public opinion polls conducted during Atlas's approach revealed something remarkable. Attitudes towards space exploration, planetary defense, and international scientific cooperation shifted measurably in just a few months. A single interstellar visitor, silent and indifferent, managed to do what decades of policy debates could not reignite public interest in humanity's future among the stars. These shifts may prove more enduring than the comet itself, influencing funding priorities, research initiatives, and global partnerships for decades to come. The encounter also exposed the precarious assumptions built into modern technological civilization. Our satellites, communication systems, and even terrestrial power grids were designed under the belief that space is a stable backdrop, disrupted only occasionally by solar storms or asteroid strikes. Interstellar visitors like Atlas challenge that premise. They introduce variables, debris fields, electromagnetic anomalies, chemical contamination that our engineering models and risk assessments were never built to anticipate. For the first time, mission planners must consider not just local space weather or known asteroid trajectories, but the chaotic legacies of objects arriving from distant stars. The implications extend beyond engineering. The legal and ethical frameworks guiding humanity's activities in space were drafted for a solar system we thought we understood. Atlas asks questions that existing treaties cannot answer. Who has jurisdiction over interstellar material that enters our system? How should potential contamination be handled? If a visitor carries artifacts, signals, or even biological material, what obligations do we owe to science, to security, and to future generations? These questions do not have clear answers, yet they demand international agreements that balance curiosity with caution, opportunity with restraint. The Atlas encounter, whether anticlimactic or extraordinary, marks humanity's graduation from a purely solar system-bound species to a participant in phenomena of galactic scale. Whether we pass or fail this test may not be evident for decades, but our responses will set precedents that echo far into the future. Atlas carries with it not only the chemistry of alien stellar environments, but also the faint radio whispers of a young civilization daring to explore beyond its birthplace. Other visitors may hear those whispers and draw their own conclusions about our readiness for membership in a wider cosmic community. In that light, October 3rd, 2025, may be remembered not as the day Mars was threatened by an interstellar intruder, but as the moment humanity began to realize that the universe is full of wandering messengers. Each comet, each fragment, each anomalous traveler may be carrying news from distant epochs and long-dead stars, reminders that we are not alone in this vast expanse. The true question is not what Atlas might have done to Mars, but what it has already done to us. The greatest danger may not be planetary catastrophe or electromagnetic chaos, but our failure to learn, to overlook our vulnerabilities, to ignore the institutional weaknesses Atlas has revealed, to neglect the urgent need for frameworks that can withstand the universe as it really is: dynamic, unpredictable, and far stranger than our short technological history has prepared us for. The silence that followed October 3rd may yet prove the most ominous sound in human history. Not the silence of interstellar space, that eternal backdrop of radio quiet we have always known, but the silence of missed opportunities. The silence of warnings disregarded, the the silence of questions too uncomfortable to ask. Atlas moves on, a ghost returning to the deep dark, carrying with it the fading radio signatures of a civilization still unsure whether it is ready for the responsibilities of cosmic maturity. Whether we passed this first test remains uncertain. The universe, patient and indifferent, will provide more opportunities. More visitors will come, each carrying the potential to alter our understanding of reality. The question is whether we will recognize them when they arrive, or whether we will continue to drown the most important signals in the noise of speculation and distraction. Sometimes the most profound revelations come not in fire and catastrophe, but in the quiet recognition that we have been asking the wrong questions all along. Atlas may not have destroyed Mars, nor triggered storms across the solar system, nor carried messages we could immediately decode. But it may have delivered something subtler and more valuable, a reminder that survival as a spacefaring species depends on humility, patience, and the ability to learn from silence as much as from spectacle. Perhaps the true danger is not that Atlas harmed us. Perhaps the danger is that Atlas saved us, and we never even noticed.